Okay. All right. Good morning, everybody. Thank you once again for joining us for our annual technical seminar on dam safety. Wanted to thank everybody that has been presenting so far. We've had such a lovely, a great conference, very good technical topics and great presentations, and then I've sure learned a lot. Alicia, did we have administrative announcements for this morning, or would you like me to go over?
Yes. Yes, I have some that I need to go over.
Okay, go ahead.
Okay, just a friendly reminder to everyone to continue filling out your evaluation forms, and we do recommend that you've already done so for day 1 and 2 so that you don't forget. Our next entry on the evaluation form was put in the chat by Preston Wilson. It's called the Risk Pry Levy in. It's the 10th one down on the list. And again, we understand that the abbreviations are a bit hard to follow. So before each presentation where there is an entry for evaluation, Preston will be putting it in the chat, and we'll try and note it too verbally to bring your attention to it. A couple just quick, more friendly reminders for the pods. Please use the admin and technical for only things that are such. And use the Q&A pod for questions that relate directly to the presentations being given and that are for the actual speakers. Again, IT recommendations for anyone that might be new today. If you are connected to a VPN, we recommend that you disconnect from it because it takes up your bandwidth. Additionally, the app version is better than the browser version of the system. I know some of you cannot use that due to firewall issues. But in the case that you are still having audio issues and you have to use the browser version, there is a backup phone number. It's located in the notes. Please remember to manually mute yourself if you do use the backup phone number. And one of the things we just wanted to remind everyone is if you quickly step away for whatever reason and you're on the phone, you can just stay muted. There's no need to call in and call out. Yesterday we had quite a bit of beeps in and out. We think we've turned that part of the system off, so it shouldn't be an issue, but just also reminding you, I know it's a little bit of a hassle to have to call in and out of a phone number. So if you need to stay on the line, as long as you're muted, that's fine as well. And with that, those are all of the announcements, and we can go to our first presenter, Joel.
All right, thank you very much, Alicia. So this morning, we are going to have a couple of presentations before our first break. So we'll have Larry Roth from Arcadis presenting on using risk to prioritize levy investments. And this was, I think, a presentation he worked with Jessica Luddy on. And so he'll introduce her probably with it. And then after that, we'll have Andy Zaleski with Ontario Power. And then during our break, we'll have a video from Sergio Escobar from California DWR on the Oroville Dam Comprehensive Needs Assessment. So with that, we'll go ahead and get started a little bit earlier. I don't think we have too many more announcements, so if we can reset the time, Alicia, and then we'll pass it on to Larry for the presentation.
Good morning, everyone. I want to thank FEMA for the opportunity to present the results of our flood risk and levy investment study for California. I'd like to, for the California Delta, I'd like to acknowledge my co-author, Jessica Luddy. She was with Arcadis when we conducted this project. Jessica is now with the San Francisco District Corps of Engineers. This is a project for California's Delta Stewardship Council. It was a state agency created in 2009 by the Delta Reform Act, and the basic mission of the council is to advance the state's co-equal goals for the Delta. That is to provide a more reliable statewide water supply and to protect, restore, and enhance the Delta ecosystem. And the objective is to achieve these two goals while protecting the Delta as an evolving place. One of the recommendations that is in the Delta plan was to establish priorities for state investments in Delta levees to reduce flood risk and to advance the co-equal goals. If you are not familiar with the California Delta, you're not alone. In about 2010, in a poll taken, fewer than 10% of Californians knew anything about the Delta. So we're going to have a little bit of a discussion on that. Today we'll talk about level of protection, and then in contrast, how we can use risk and risk analysis to develop investment strategies. We have 5 tolerable risk guidelines, and we'll go through and describe how that was done. Before we really get to the Delta, we need to understand a little bit about water in California. Most of the precipitation falls in the north part of the state and in the Sierra Nevada. And then that water is collected and used. The agricultural demand is in the Central Valley, and the urban demand is in the Southern California and the Bay Area. So the water has to be moved from where it falls as snow and rain to the places of use. That means it has to go through the Delta. The Delta is really the hub of the state's water delivery system. It's the confluence of the Sacramento and San Joaquin rivers. It's about 60 miles northeast of San Francisco. And to illustrate its importance, 27 million people in California drink water from the Delta, and it's used to irrigate over 4 million acres of farmland. And in addition, the Delta ecosystem really depends on healthy and consistent river flows. The pre-1800s, before European settlers arrived, was really quite an amazing place. It was called often the American Serengeti. Nearly 1,000 square miles of wetlands and tidal marsh that supported over 500 species of fish and wildlife. And it would periodically flood that would create a vast inland sea in the Central Valley of California. But today's Delta is largely man-made. It's important to the state because of its agricultural resource. And there are highways, railroads, pipelines, utilities of all kinds that crisscross the Delta and are very important to the state of California. It's rich in fish and wildlife, and of course that stimulates recreation and ecotourism. And the Delta is a unique place within the state that has values that should be preserved. The Delta occupies about 1,200 square miles. It comprises about 150 islands and tracts, and these are islands and tracts are surrounded by about 1,100 miles of levees. And notably, there have been about 158 levee failures since 1900. The Delta is home to about 500,000 Californians. It's affected by subsidence caused by the oxidation, compaction, consolidation, and wind erosion of extensive peat deposits, and some of the areas of the Delta are as much as 25 feet below sea level. As a result, most of the land in the Delta is below sea level, and the levees in the Delta, the 1,100 miles of them, do function as dams with water against them 24/7, 365. In addition, we have to account for potential sea level rise. The projections are nearly a foot to 2 feet by 2050 and about 5 to 6 feet by 2100 at the Golden Gate Bridge. This translates to about a foot in the West Delta, and that tapers to zero near Sacramento in 2050, and we accounted for that in our calculations. The levees are critical to the water supply. The water from Sacramento and San Joaquin rivers flows across the Delta to pumps at the south end of the Delta, which then pump water into the state and federal systems for distribution through ag and urban areas. And the westernmost islands are critical because they impede brackish water from entering the Delta due to tidal flow. These same western islands are also close to the high seismic area of the San Francisco Bay, and a number of the westernmost islands are susceptible to failure by earthquake activity as indicated on this particular diagram. The entire delta faces flood hazards, and most of the islands, which you can tell by the deeper color blue, face less than a 1 in 50-year level of protection. And of course, the levees face ongoing threats from earthquakes, subsidence, from sea level rise, and then from climate-driven changes in hydrology. It's been estimated that it will take $1 to $3 billion to fix the levees, and we're currently spending about $20 to $30 million per year on levee improvements. But there is a real need to prioritize spending, even if all the money were available at once. We simply couldn't do all the work at one time, so we want to be able to do the work in some priority manner. The first California state engineer, William Hammond Hall, is noted as saying there were two types of levees: those levees that have been overtopped by floodwaters and those that will be overtopped by floodwaters. This is important to keep in mind as we look at our current guidance, which is usually the 1% annual exceedance probability flood, better known as the 100-year level of protection. And of course, this generally forms the basis of certification and FEMA accreditation. But there are limitations with the level of protection approach. It focuses on the hazard and does not account for the consequences of flooding. There's an implication that risk can be eliminated. It favors structural solutions, and it's hard to measure risk reduction or cost effectiveness of various solutions. And this slide illustrates another question that's difficult to answer in the levee, in the delta. Which should we fix first? Those levees that protect agricultural land, or those that protect people, property, and infrastructure? The level of protection also importantly ignores residual risk, which is the flood risk that remains after all appropriate actions have been taken to reduce that risk. The structure on the right has a lower residual risk because a slightly bigger flood will bring shallow inundation and minor damage. The structure on the left, however, if it faces a slightly larger flood, the levee could overtop and the damage would be extensive and the failure would potentially be catastrophic. So ignoring risk has many potential adverse consequences to public safety, to land use decisions, to how we make infrastructure investments, and to our own personal preparedness. So you're all familiar with common street definitions of risk. That is the possibility that something bad can happen, and there's also an indication that threats perhaps could be identified, evaluated, mitigated. But in risk analysis, we use a more precise definition, and that is risk is the probability of occurring and times the consequences should that event. Have you seen this before? And I apologize for some of this repeat.
Sorry, one quick second. For those of you on the audio line, as a friendly reminder, you must mute yourself. I repeat, you must mute yourself. Thank you so much. Sorry, Larry, go ahead.
Hey, no problem, thanks. So you've seen this, the information on this slide before. To calculate risk, we have to understand what the hazards are and how likely they are to occur. We need to know what is in harm's way and how vulnerable it might be. And we have to know how any intervening structure, such as a levee, will perform. But the risk analysis offers the ability to answer questions about just what is the risk and why is it there, which risk is the greatest or the most urgent to deal with, and if we deal with that risk, how much residual risk will remain. The risk analysis enables better understanding of risk and better communication. It helps us decide if additional risk reduction is warranted and help identify actions that can be taken to address the most urgent risk. You've also seen the information on this slide before. The tolerable risk is the level of risk that people are willing to live with in order to secure certain benefits. And as you know, it has a range of tolerability, everything from risks that are totally unacceptable to those that are very broadly acceptable. And it's not that difficult a concept when you think about it in terms of our everyday use. We make tolerable risk decisions in our everyday lives. We select the amount of insurance that we need or want to have for our life and for property. We also can assign deductibles that we choose for our own use. Whenever we get in our cars, we can buckle up to reduce the risk of being seriously injured in an accident, and we can also reduce the risk of getting a ticket for failing to buckle up. And we're all faced with the decision of buying extended product warranties or product protection plans when we buy electronic products such as cell phones. The Corps of Engineers has established a number of key principles for tolerable risk. The first and probably most important is that we should hold life safety paramount. And to do this, we need to understand the risk. We need to build risk awareness and then monitor and manage that risk. We use that to find cost-effective solutions that are both socially and environmentally acceptable. We need to take actions that are commensurate with the risk and ensure that those actions and that risk is openly and transparently communicated. We need to learn and adapt and also do no harm. But given that risk cannot be ignored and that absolute safety cannot be guaranteed, we do need to understand how to set limits for tolerable risk. And setting limits is informed by analysis and by expert judgment. It considers individual risk and societal risk, and it also considers equity as we distribute that risk. ALARP is the usual goal. ALARP is what can reasonably done without spending an inordinate amount of time, money, or resources relative to the risk reduction benefits. So there's 4 basic steps in applying the tolerable risk guidelines. In step 1, we need to characterize the risk. This requires an inventory of assets, an identification of hazards, and an assessment of vulnerabilities. In step 2, we can identify options to be able to reduce that risk, and that might include structural options like levees or non-structural options like improved evacuation systems and warning systems for potential floods. Risk analysis allows us to quantitatively evaluate those options, and we can compare for cost effectiveness, we can evaluate trade-offs, and we can assess the residual risk remaining to determine if it's tolerable. Step 4 is often downplayed or overlooked, but it's really important. It's the things that we do in operation and maintenance that allows us to continue to monitor for potential changes and to either adapt to those changes or start the cycle all over again by doing a recharacterization of the risk. The common measurements of flood risk are loss of life and damage to property. Loss of life is expressed in expected annual fatalities, and that's the number of individuals exposed to floodwaters. It's affected by warning time, depth and velocity of water, the rate of rise, the temperature of the water, and so on. Damage to property is the annual cost of flood damage. It's generally dependent on flood depth. The 2 maps shown on the slide are EAF and EAD for the Netherlands. When it comes to the Delta, though, we need to reduce risk to the state interests that have been identified in the Delta Plan. That is, of course, life and property, but it also is risk to our ability to advance the co-equal goals of protecting water supply and enhancing the Delta ecosystem, and also protecting the Delta as a place. So to do this, we established 5 different risk metrics for the Delta. They include, obviously, expected annual damages and expected annual fatalities. We also developed risk metrics for disruption of the water supply statewide through the Delta, harm to the ecosystem in the Delta, and damage to Delta as a place. So how do we use these tools and metrics to analyze risk in the Delta? So taking the big picture view, if we look at current flood hazard, which I showed earlier, basically about a 1 in 50 year level of protection, if we do nothing, that flood hazard is going to double by 2050. So it's clear that really something must be done. And if we look at the results of the risk analysis, on the left-hand side, you can see the expected annual fatalities. The darker islands are those islands with the highest potential expected annual fatalities. They tend to be, the population tends to be concentrated in the north part of the Delta near Sacramento, and the southeast part of the Delta near Stockton, so it's not surprising that we see higher EAF in those areas. On the right-hand side of the slide, you see expected annual damages, and these tend to follow where people are. Infrastructure, housing, businesses, and so on tend to congregate around people, and so the expected annual damages are also higher near Sacramento and near Stockton. The water supply disruption was a very difficult metric to establish. It turns out there isn't an easy cost metric. The disruption of the water supply depends on a huge number of factors, including the time of year that it might occur, whether there's storage, ample storage in the upstream reservoirs, and a number of other factors. And so we chose to use 3 proxies. The first is shown on the left, which is the islands that protect water quality in the Delta. These are the islands that I mentioned earlier that are the cork in the bottle that prevent brackish water from entering the Delta. In the middle, you see the islands that are important to create that or to maintain that freshwater path across the Delta that brings water to the pumping stations at the south end of the Delta. And then on the right-hand side are islands that house important water supply infrastructure, that it might be aqueducts or pump stations that are important to the water supply. And combining these, we came up with the metric, which is really a dimensionless score that identifies those islands that are most at risk to disrupting the water supply, from reduction in the salinity barrier, damage to the freshwater corridor, or damage to the water supply infrastructure. The left-hand side of this slide shows the potential damage and harm to the ecosystem. So the darker islands are islands that where the ecosystem could be significantly harmed by flooding. But we also took advantage of looking at that to look at areas that could serve as unlevied high-value tidal habitat. And if these levees on the right-hand side were improved or built higher, we'd actually have a lost opportunity in terms of tidal habitat in the Delta. And then for damage to Delta as a place, we chose 3 proxies. On the left-hand side, it shows the potential damage to prime agricultural land. In the middle, we assessed damage to public roadways from flooding in the Delta. And on the right-hand side, we assessed damage to legacy towns within the delta. So the risk management, risk analysis based on a snapshot in time using best available data has given us a powerful tool to evaluate the effectiveness of risk reduction and the ability to compare trade-offs. There aren't any risk-based standards or guidelines to determine the tolerable level, and that tolerable level of risk needs to be decided by those most affected, and risk analysis is a good way to communicate to the stakeholders and public that are concerned about flood risk. Well, how do we put this all together? If we've got now 5 different metrics of risk, risk to loss of life, obviously measured in number of people that might be killed during a flood. We have flood damage that's measured in dollars. We have water supply disruption that's dimensionless. We have harm to the ecosystem, which is in acres, and then damage to delta as a place, which is also partly dimensionless. So in order to put this all together, we created an analytical tool that we call the decision support tool, and this enabled us to mix risk components with these different metrics, and it allowed us enables also to apply weighting factors that are based on community values. So in other words, if we thought life safety was twice as important as all of the other factors, we could assign that value. Or if we didn't care about, say, risk to water supply, we could zero that out. And this allowed us to visualize and communicate how these risks could be affected depending on how we chose to weight them. The tool also enabled us to evaluate the effectiveness of risk reduction actions and to compare trade-offs. This was, of course, very important to inform decision making, and the tool was also built so that it could easily accommodate updates for changing conditions. So stepping through use of the tool, the first part is to characterize the risk, and we have to populate the tool with an inventory of assets, hazards, habitat information, and so on. And then we can play what-if scenarios by identifying and evaluating options. We can look at proposed improvements. We could add factors from climate change, population and growth, and so on. And with this loaded, it formed the basis of what we call deliberation with analysis, and that is stakeholder deliberations to make a determination of the actions to be taken. And then finally, we could prioritize improvement using the results from this risk analysis and decision support tool. And here's the final result of the Delta Levees investment strategy. The islands in bright red are those that were determined to have the very highest priority for investments to improve levees, to reduce risk. I will tell you that life safety was the dominant factor, although it turned out that a fairly balanced distribution of weighting really came up with about the same kind of results. The other colors show islands that have a lower priority for investment to improve the levees. So applying the tolerable risk guidelines to the Delta allowed us to recognize what the residual risk was. We were able to involve the stakeholders that are most affected by the risk, and it gave us a way to communicate effectively with those stakeholders and improve their understanding. We could play what-if scenarios to evaluate trade-offs, and we could use that information to determine where and when to act. So the tolerable risk guidelines enabled clear communication to decision makers, stakeholders, and the public. We identified the areas of highest risk, and we placed the appropriate focus on life safety. But we were also able to look at the risk metrics to water supply disruption, ecosystem habitat harm and then damage to deltas of place. So this was provided a very open and transparent basis for prioritizing investments in levee improvements. And I would close then by just sharing some key stakeholder comments. An organization called Restore the Delta is one of the key public groups within the Delta, comprising Delta residents. And of course, they tracked our progress through the Delta and levees investment from the beginning all the way through to the end. And at the beginning, they were extremely skeptical, and this is reflected in their letter commenting on the Delta levees investment strategy, which was included in amendments to the Delta plan. They had perceived that really they thought the goal of the council and the state was to get rid of the low value islands in the Delta, but they soon came to appreciate the approach that the council had selected to take with risk analysis and concluded that they found much to appreciate in that effort. And finally, they concluded that they understood the necessity to prioritize levee investment. So it was very successfully communicated to the key people in the Delta. I want to thank you for the opportunity to make this presentation, and be glad to answer any questions.
Thank you very much, Larry. That was very informative. I think a lot of people, like you mentioned, don't necessarily understand that California has a delta, let alone levees. So very good information here. We did get a couple of questions in the chat, and I'm just going to pick out a couple of them. We do have time, so I'll ask maybe the first one from Chris. It says, how long were the agricultural lands assumed to be damaged? And levee settlements, are they just raised also for sea level rise? So that we can answer that first question.
Could you repeat that? I couldn't hear it quite very well.
Okay. How long were the agricultural lands assumed to be damaged? That's the first part.
Well, I'd have to go back and check, but we assume that they would be out of production for a full year, and then it was a slow return to full production over an additional 2 years. So basically, we assume that the damage had about a 3-year effect following the flood.
Mm-hmm. And then the second part, I think, was referring to the type of damage. Is it levee settlement, or were they just raised also for sea level rise?
The type of damage to agricultural, I assume that's what the question is. And
to the levees?
Sorry?
To the levees that led to the raising of the levees?
We looked at both the potential for static failure of the levees and seismic failure of levees, but the dominant mode of failure was overtopping due to floods in the Sacramento and San Joaquin. There's very little freeboard for many of the levees. So the dominant failure is considered to be levee overtopping.
Mm-hmm. One last question here. This is from Preston. Explain how did the weighting factors come about?
How the weighting factors come out? This was I hesitate to say it was a complex process, but basically we looked at each factor individually and identified those islands that were most at risk for each of the 5 factors. And then when we fed that information into the tool, we were able then to combine those different lists of high-risk islands and rate them. So it was a bit of a complicated process to put it all together, but basically you had to look at each of the individual metrics by themselves, and then use that to develop a list of priorities, and that involved identifying thresholds. For example, the metric for expected annual fatalities, we had to what the minimum acceptable or the maximum acceptable, I guess, your perspective, and then group those islands that had very high risk to people for life loss, and had moderate risk, and so on. Putting all that information into the analytical tool, we were manipulated in various ways to be able to assign different weighting factors. And I should add, in my presentation, which is going to be available, I listed a number of references. Quickly scroll through those, so there's much more information can be gained. And, the final reports on the Delta Levees investment strategy are available on the Stewardship Council website. There's a report methodology and a report on the results, and that describes in detail the process that was used to arrive at our ability to mix these, come up with a defensible list of priorities for not.
All right. Well, thanks again, Larry. Thank you for the presentation. Just once again, just to mention, as we're going through the presentations, if you have questions, please type them in the chat, the one that's for the Q&A, and we'll ask them at the end of the discussion. And if we don't get to those, we'll ask the presenters to maybe go in and answer them in the chat, or if they're going to be on the panel for Friday, they may answer them at that time. But we'll go ahead and get started with the next presentation by Andy Zaleski. And he'll help me pronounce his last name. I apologize, I'm butchering it. But it's on risk assessment and dam safety. I'll pass it along.
Okay, you pronounce my last name correctly, thank you. The first name is challenging, definitely.
I didn't even touch that one.
Okay, first of all, good morning to everybody, and thank you for the opportunity to have this presentation and be able to talk to you. So if you go to the next slide. Right, it's the outline. I want to talk a little bit about the past because it is important for us to realize what was the journey from the very beginning to the state of the art we are today. So I will be talking a little bit about 70s and 80s, and then about present methods and approaches, some new emerging trends, and future focus, what we should be doing in the future in order to make next steps to progress to next level. Next slide, please. Okay, the next one. So the beginnings go essentially to the very late 1960s and early 1970s. Here you can see the study provided by Ellingwood and Ang. It dates back to 1972, and it was one of the first clearly identified concept of using risk in civil engineering. It was not especially for dams, it was for civil engineering. And the authors indicated that the rational approach to safety involves consideration of the concept of acceptable risk. They were talking about acceptable risk. Today we prefer to talk about risks which are tolerable. But I think this was a very important observation of these two authors. Next one, please. Okay, we're looking at another report by Yuseman, Tang, and Ang, and they went even a little bit further. This is a report which was issued in 1973. They indicated that the expression of safety in terms of risk makes it possible that the decision analysis can have a chance to approach something which we will call optimal design. Next one, please. McEwen. It was 1979. He quite clearly observed that a major step toward adopting would be adopting a design systems which allows us to assess the risks for all design factors which involve uncertainty. So today we think that it is quite obvious, all these three statements which I presented on the last three slides. But we have to remember that we went quite a long way, and at the time when these observations were made, they were quite revolutionary. Next one, please. A report by Prendergast. The important observation of this report is indication that there is no systematic way of analyzing the degree of uncertainty without inclusion of risk. And he also stated that in realistic sense, the safety of dam is a matter of acceptable risk. Otherwise, any decisions which we will make can be not even close to good decision or optimal decisions. Next one, please. Which techniques were used in the 1960s and 70s? They were quite limited, and they included the methods of classical reliability theory, which came from structural reliability theory, some applications of first-order probability theory, and there were also some attempts to use what at that time was called decision trees, but which is in today's terms would be closer to fault trees. So this is in terms of analytics. In terms of evaluation of identified risk, there were some inputs from Bayesian decision theory, but the general concept, which is presented on this chart on the right side of the slide, is quite similar to what we apply today. We have the overall risk assessment, which is separated into two parts: risk determination And risk evaluation determination includes identification of risk and risk estimation. The part which relates to evaluation looks slightly different. I mean, it has risk aversion and risk acceptance. Today, we prefer to talk about risk evaluation in terms of risk tolerability criteria. Of course, both this concept of acceptance or conditional acceptance and risk aversion are present in developing the risk evaluation criteria, but we approach it slightly differently. But in general, the concept as developed in the 1970s still applies today. One thing which I should probably mention at this time, because I will be talking more about analytic methods, is that my entire presentation has a very specific focus. When we are talking about risk assessment for dams, we may talk about it using different contexts. We have application in terms of portfolio of dams risk management and risk assessment. We can talk about prioritization. We can talk about even simpler methods like risk indexing. What I would like to focus on in the rest of my presentation is detailed or comprehensive analytic methods of risk identification and risk analysis. I won't be talking about the evaluation and decision making at all. This is a separate issue, and as I said, I will be concentrating on analysis part of the risk assessment. Next one, please. 1980s. We have an imported report coming from Cheng, Yen, and Tang when they approached the methods of quantitative analysis of overtopping risk for dams. And he presented a specific method which is fully developed in this report. Next one, please. Still 1980s, and this is quite important developments, five-step risk analysis process, and we have here a report from Utah State University. The primary author is Howell, but this work was further development of approach which was presented in 1978 by David Bose, which used a four-step analysis process. This is the next evolutionary step. And why is it called five steps? We have these 5 steps on the diagram on the left side. We have start with an event or failure mode, what we call today failure mode. We have something which we call system response, and the outcome. The outcome is interesting because what we have here, you probably cannot see that, but I will tell you what we have. We have dam breach, we have no dam breach, or we have partial dam breach. And the rest of this diagram is related to the other part of risk analysis, which is consequences. Exposure, which is important when we are looking at life safety issues, and then consequences in terms of, they can be in terms of all different types of consequences. Next one, please. Now, let's come to the present. Next one. And This is extremely important document, which was published in 1986. It is called Guidelines to Decision Analysis, and it was developed by Bureau of Reclamation. And the purpose of the document was to outline a decision analysis framework, which includes the concept of adverse consequences from dam failure and the probability of the failure occurring. Next one, please. So this chart presents the overall concept of the guidelines. It's very general at the top. It defines the problem, then characterizes site conditions, and it goes through different steps, ending with assessment of consequences. Next one, please. So this is a top portion of this diagram, which was presented on the previous slide. So we start with the definition of the problem. We characterize the site conditions, which means characterizing the dam itself, but also the surrounding dam environment. The next step is identification of potential loading conditions, and it can be hydrologic loading, it can be seismic loading, it can be anything which presents hazards to the safety of the dam. And the next step is determination of system response. And as you have already seen on one of the previous slides, the system response can be the dam fails, the dam doesn't fail, or we have partial failure. The partial failure is not defined precisely, and it is not entirely clear in the document how this concept of partial failure can be applied in actual risk analysis. What I want to stress out here is that we have very clear separation between characterization of loading conditions and how the system responds to these loading conditions. It is quite clear from this diagram that the loading conditions are predetermined, and they are one of the first steps in the analysis, and there is no feedback link between system response, especially what can be important here is partial failure, between system response and loading conditions, which can be modified depending on how the system behaves or responds. Next one, please. The first application of this framework was Tongue River Dam in the state of Montana, and you can see from the diagram that what was used here is what today we will call event tree. I will talk about that a little bit later. Next one, please. So we are coming to the event tree.
Andy, apologies, one quick second. It sounds like someone is unmuted on the phone line. As a friendly reminder, please mute yourself.
Mm-hmm.
We're definitely getting some feedback now.
Okay, can I continue?
Yeah.
Okay, so now we are coming to event trees. And the event tree, which in not exactly the same form as we're using today, were used in Tongue River study and recommended by the ACER report, they became a primary analytic technique in risk assessment for dams. And the event tree approach is used extensively in the United States. It is used in Canada. It is used also extensively in Australia. Why is it so attractive? Well, there are several features of event trees which make them attractive. They can easily display chronological or temporal order of events leading to the failure. They are intuitive in the sense that we are moving through time from left to right, and we can see the sequence of events and we can see the logic. They can be as detailed as we want them to be. They can be very detailed, they can be short, or they can be extensive. It depends on the approach of the analyst. They can display dependencies between different events in the order in which they occur. Very good tool for communicating and understanding assumptions. They can be used to communicate people which do not have as technical background as usually risk analysts involved in dam safety assessments. And from the analytic point of view, they are easy to use. There is a software which is available, and there is many different platforms. But essentially, event tree analysis can be also developed in-house using just the popular spreadsheets. Next one, please. So if they are so good, is there anything which is not so good? Well, first of all, they are based on an assumption that the behavior of the system, analyzed system or analyzed dam, can be explained by a series of related events over time. And it is a linear series. From experience, which is coming not just from dam engineering industry, but from other industries which are using or were using event trees for safety considerations, we know that they work relatively well for simple systems, but they are not capable to properly reflect how the complex systems behave. They cannot account for nonlinear interrelations between individual events, and they are quite inefficient in reflecting poor performance of humans, which are involved in usually in operation of the existing system. So there are limitations, and these limitations have been recognized. Next one, please. Are there any emerging trends? And the next one, please. One of them is stochastic simulation. And we have two types of simulations. One of them is a stochastic event simulation approach, where it is with I would say very good results used for analysis of overtopping failure modes coming from excessive hydrologic loadings. So the approach is relatively simple. We start with selection of storms over the watershed of interest where the dam is. And we go through a process of not maximization, but stochastic generation of storms with different probabilities of exceedance. These storms are then fed into a watershed model, which transforms the climatic input data into inflows, and these inflows are then run through the reservoir and through the dam, and observed over a period of time, so we can generate as many events as we want to, and then simply calculate the frequency of events, frequency of overtopic events from the observation, how the system responds to the simulation. And a few years ago, there was an excellent presentation at one of the ICOT annual meetings related to stochastic event simulation for the Campbell River, one of the hydroelectric system in British Columbia, Canada. Next one, please. Continuous stochastic simulation approach. This is a slightly different approach, and it's much more resources intense, but there are definite benefits from continuous simulation. And it is coming from the nature of the hazard presented for dams and river systems. Water is coming to the dam all the time. We cannot turn it off. Whether we like it or not, it is coming. It is coming in different quantities over time, and it cannot be stopped. So what it means is that the hydrologic hazard is present at all times on a continuous basis. It is not an intermittent hazard, like probably the best example would be seismic event. Shit. Can you hear me?
Yes, we can.
Okay, I lost connection for about 10 seconds.
No, we
But
can.
I am glad Okay, so I can continue. So the idea of continuous stochastic simulation is essentially similar to stochastic events. The difference here is that we generate long series of weather or climate inputs, run it through the watershed model, and produce inflows, and simulate the behavior of the system under this simulated inflows. Next one, please. So I want to show you one of the examples which was applied in Canada, and this is one of the systems of Ontario power generation. On the left side, you can see the complexity of the system, number of dams. On the main stem, there is 2 control dams and 5 generating stations, all belonging to Ontario power generation. But on the tributaries, there is a large number of smaller dams belonging to different owners. So there is a challenge in operating the system in a best possible way, because as I said, there are different owners with different priorities and different practices. Next one, please. So the simulation went in 3 general steps. First was application of the stochastic weather generator model. It was a model capable of addressing the generation at multiple climate stations, multiple sites. The time series produced were in the range of tens of thousands to hundreds of thousands daily values of precipitation and temperature. This time series were fed into HEC HMS watershed simulation model, which produced the hydrographs, produced the time series of daily inflows. And this time series of daily inflows were fed into dynamic system model. Next one, please. So this is a better look at the model. So the inflow is coming all the time, day by day, for this, as I said, hundreds of thousands of years. And from time to time, this operation can be disturbed. The forecasts used for operation can be wrong. The human decisions in terms of releases from different reservoirs can be not properly implemented. The plans how to arrive at these decisions can be wrong. There may be no possibility of site access, which prevents from operating stop logs. The equipment can fail. Generating equipment can become unavailable. So all of this, if we look at the history of the simulation, the red line on the chart is the actual water level. The top blue line is the top of the dam. When it is exceeded, we have overtopping at the dam face. We can see in the right top corner the instance when the red water level is over the top of the dam, and this is overtopping failure. So if we run the simulations for hundreds of thousands of years and count the number of overtopping instances, we will get the frequency of overtopping, which is a very good approximation of probability of overtopping. Next one, please. Okay, that shows an example how this works. We're looking at one of the generating stations on the main stem of the river. The turbine flow is presented with the help of the black line, and we see at the very top of this diagram that all of a sudden the turbine flow rapidly goes down. We have a comment on the chart below that unit 3 was out for 4 days and passing only speed or no-load flow. So the gates or stop logs had to kick out, and we increased the spill from 0 to a level which compensated the lack of the turbine flow. Next one, please. Example of results. We can see here different risk presented by different failure modes: overtopping, piping, slope stability, and risk of concrete failure. And overtopping risk is presented by these blue dots and blue lines. Next one, please. Adding additional discharge capacity of about 10% of actual discharge capacity brought down this blue dots and blue lines. It doesn't have a very huge impact on the overall or aggregated risk to the dam, because you can see from this chart that the risk is driven primarily by the yellow dots, which is concrete stability. Next one, please. And dams as systems. This is an important topic which is coming to the front of our considerations in risk assessment. Next one, please. One of the first documents on risk assessment for dams, which was published by UNCODE in 2003, defined dams as systems along the, I would say, the traditional lines of defining systems. Next one, please. In 2013, DEFRA, which is one of the United Kingdom environmental agencies, issued guidelines on risk assessment for dams. And this is an important document because the concept of dams systems was not only very explicitly recognized, but defined in a much more defined way, defined in a much more precise way as compared to the previous documents. So therefore recognized that dam as a system has physical components, has operational components, but it also has very important part, which is human agency. Any of these components or features can fail, not necessarily has to be physical feature which leads or originates the failure. Next one, please. So, in general terms, dams as systems can be presented as a system of 4 different subsystems. Natural, which is the watershed, lakes, rivers, all the physical connections. Technical subsystem, which is all the hardware we put in, the structures, dams, equipment, the surveillance networks. We have also management system, organization of the owner, and the plans, procedures, and processes. And on top of everything, we have political and socioeconomic subsystem, which can put certain pressures on the management subsystem and technical subsystem. Single dam versus multiple dams, the complications of these different subsystems are vastly different. Let's go to the next slide. So we have interconnections between these different subsystems, and the arrows here show kind of very slow dynamics, which are very often taken place over several years. And we have fast dynamics, which are also affecting how the system operates and what are the interconnections. We also have feedbacks in terms of how the system control is taking place, which of course can affect the safety. Next one, please. The future. Next one. What's the future? And I want to quote Edwin Thompson James, famous physicist who also was instrumental in developing the concept of applications of subjective probabilities in different areas of physics and engineering. And what James said, that as knowledge advances, we will be able to develop better and better models. These models will be able to reproduce more and more features of the real world, and they will be better in the sense of accuracy. Nobody knows whether there is some natural end to this process. So what we should expect is that any model we have now, which we were able to construct and implement, will be replaced by better and more complete ones in the future. And this process never stops. Next one, please. So, if we agree that we cannot stop the progress, and we shouldn't be stopping the progress, what are the key areas where we can make this progress, and we should make this progress? In terms of analytics, there is probabilistic characterization of hazards. This work is ongoing, and every year is bringing more new techniques and tools which are better than the previous ones. There is a need to further develop failure modes and failure mechanisms analysis. We are now, to a large extent, rely on potential failure modes and effects analysis, but there are ways how this process can be improved and should be improved. The one area which is showing very little progress from the start of applications is improvement in the practice of elicitation of probabilities from experts. We unfortunately are still missing modeling support for some of the failure modes, which are critical for safety assessment of dams, and we have no other option but to use experts and try to get the best characterization of in probabilistic terms. However, the methods which are using essentially did not evolve in any significant way for the past 20 years, and there is a possibility of improvements here. It requires some hard work and putting of resources into this problem. In the terms of risk evaluation and support in decision making, we need more engagement of experts from non-technical disciplines into development of better means of characterizing other consequences than life safety, socioeconomic, environmental, cultural. This is important. If we don't measure the consequences in a proper and appropriate way, all our decision making can be negatively affected by that. And lastly, we also need to engage all stakeholders into development of new framing of other consequences: environmental, socioeconomic, life safety, and health. At the moment, we rely extensively on some simple life safety consequences. We need to move into other areas, and in order to do that, we have to engage other people. It should be people who are mostly affected, but it is also regulators, politicians, and this is something which needs to be done. The next one, please. And there is no next one. That was the last one. Thank you very much for your attention.
Thank you very much, Andy. I appreciate your presentation. That was definitely a lot of information, a lot of good points there, particularly this expert elicitation and risk analysis. I think is pretty critical. Not to understand exactly how to do that. So we have a couple of questions, comments on here in the chat, and I'm gonna pick the first one and then get to the second one. So like, I think this question maybe go quickly. Is it practical to use this for new dams, or is it more realistic to use it for only existing dams?
Well, the examples I was we are looking at two different problems, and I think that the nature of risks which we are facing when operating existing systems and the nature of risks which we have to take into account for designing a new dam, they overlap to some extent, but there are some very specific issues which are present in one area and are not present in other. There are two very good ICOLD bulletins dealing with this issue, and the title is Dam Safety Management. Part one is dam safety management in the phase which goes before the dam is operational, and that accounts for design, construction, and commissioning. And there is very detailed explanation why the nature of the risks facing the designers and constructors are slightly different than the risks facing the operators. The second part is the dam safety management in operational phase. So there are two separate bulletins. They are available to everybody who wants to access them. Everybody who belongs to USSD can have access to a free copy of any ICOLD bulletin. So if anybody is interested in this part, how to deal with the risk issues in pre-operational phase versus operational phase, I would encourage you to have a look at these two bulletins.
Thank you. I think we just about out of time, so we can get sort of caught up. But the last question I was going to ask you, and I think it's probably good to present it to the panelists tomorrow, is regarding human errors. And I think Eric Halpin mentioned numerically modeling human behavior is not recommended, particularly for engineers. I think that's a topic that we can probably explore at the panel. I don't know if you'll be available for the panel, Andy, tomorrow?
Yes, I can be available if needed, of course.
Okay. All right, we'll stop there so we can get caught up a little bit here as we go to break. So thank you very much, Andy. And
I'd like to thank everyone for giving us the opportunity to share with the group the work that we completed over a 2-year period for the Oroville Dam Safety Comprehensive Needs Assessment. I was the project manager for that effort, and like I said, it's a lot of great work that went into it. So first of all, after the 2017 incident up in Oroville, executive soon realized that, hey, you know, this facility it's over 50 years old. and we should really do a comprehensive assessment of the overall complex. So that June, the department sent letters to both FERC and the California Division of Safety of Dams, which regulates the California dams, basically stating that DWR was going to initiate this effort as soon as consultants and DWR personnel that were working at the spillway reconstruction activities had some time available to initiate this effort. A letter or letters in the early part of January were sent to both FERC and DSOD, basically informing them that we were ready to commence that effort, and basically what we were concluding, or at the conclusion of the comprehensive needs assessment, that we were going to have a list of prioritized dam safety and operational reliability needs for DWR management to evaluate and subsequently schedule those projects through normal practices and procedures. So what was our mission? Our mission was quite simple. Identify and prioritize dam safety and operational needs. And then once we had those needs identified, the next thing was to develop measures to reduce those risks, and then follow that up with putting a list of plans or projects together for management to prioritize or implement in the future. So what we used was a 6-step well-known process for water resources engineering studies. The 6 steps are, you first identify objectives, constraints, opportunities, and needs for the project. Once that has been completed, the next step was to identify measures to address those needs. Follow that up by combining the measures to formulate the plans. Evaluate those plans with agreed upon metrics. Compare the alternative plans, and then recommend plans for consideration. So we did all that through the CNA process. So the Oroville complex it's a fairly large facility, and one of the things that we did was to break it up into manageable sizes. Also looked at what facilities, major facilities, made sense to split them up accordingly. There are 2 items here. The operational needs assessment, that's more, that's not a structural view of the project, but it's more an operations, how do we operate the facility? And then the task 6 has to do with the instrumentation and monitoring. So I'll quickly go over the various tasks, or we often call them swim lanes. Task 1, the spillway capacity restorations. One of the things that we wanted to do is see what improvements or enhancements would be needed to restore the capacity of the overall spillway, not only the gated spillway, but also the emergency. Task one focused more so on the emergency spillway, and we wanted to make sure that we could pass the standard project flood for the facility. Task two, as I briefly mentioned, once the other tasks, task 1, 3, 4, and 5, once they came up with measures and subsequent plans were developed, the operations team took a look at those plans and looked at what operational potential modifications would be needed to be able to operate the facility. Task 3 primarily has to do with the gated structure and its reconstructed spillway. So we looked at potential failure modes associated with that. Task 4, the low-level outlet enhancement. Oroville has 3 existing ways of three existing ways of releasing water at the low level. So we looked at potential failure modes associated with those facilities. Additionally, we looked at what additional low-level facilities could be constructed. Task 5 looked at not only the main dam. There are 2 saddle dams on the complex. So Task 5 looked at potential failure modes associated with the dams. Task 5 looked at all the historical instrumentation and monitoring, and also as part of that effort, looked at what additional instrumentation or monitoring could be implemented as part of this project. Another thing that we did early on, we hired numerous industry experts. So we put an independent review board together. So that it consisted of 5 members, and their job was, in essence, to conduct independent technical reviews of our key deliverables. We met with the independent review board a total of 10 times throughout the project, and they added significant value in technical and communication perspectives. The IRB also provided updates to our state water project contractors. These are our stakeholders, and also participated and provided updates to the ad hoc group at meetings that we had. For the most part, following every IRB meeting, we had meetings with the state water contractors and ad hoc. Last year, after COVID hit, it kind of put a spin into our routines, and we had a change course a little bit. Moving on, The ad hoc group, as I mentioned previously, it in essence was comprised of local leaders and residents of affected downstream communities. Some of the individuals included the Butte County Sheriff, state and federal elected officials, representative from the Oroville Chamber of Commerce, individuals that basically looked at or are involved with recreational activities or they're part of an advisory committee for the Oroville complex and others. As I mentioned, we, for the most part, were meeting every time after we met with the IRB, but as a result of the COVID last year, we actually ended up meeting only 8 times with this group. Our biggest challenge with the ad hoc group was how to communicate something highly technical and put it in words that the general public could understand and comprehend. So trying to communicate risk, and project outcomes as we were working with the group was, I would say, one of our biggest challenges. So we, as stated before, we initiated the CNA in January of 2018.
Thanks, FEMA, for the chance to talk about this topic. I want to first mention that FEMA was able to make my presentation 508 compliant. So if you're not familiar with that, 508 compliance makes your presentation accessible for people with disabilities. And that really demonstrates the principle of equity, which is important to the topic we're talking about, decision making. So equity is not necessarily treating people the same, but treating people fairly and risk-informed decision making. That's very important, in particular to how we address individual loss of life risk. So kudos to FEMA for that. So 2020 was a record-breaking year. There's an agency in the United States called NOAA, and it tracks natural disasters that cost $1 billion or more. And so 2020, we saw 22 separate billion-dollar weather and climate disasters in the United States. So that broke the previous record of 16 that occurred in 2017 and 2011. The 2020 cost were $95 billion, with Hurricane Laura and the Western wildfires as the most costly events. So in this kind of environment of rapid change and high risk, good decision making becomes even more important, and that's what I'm going to talk about. But I'm going to ask you to think about, as we go through this, the whole idea of the $95 billion, how did that change how we make decisions? So think about that as we go through. Great. All right, so this is the stuff I'm going to talk about. And I'm a little bit chagrined to say I'm not going to talk that much about risk. I'm going to talk more about benefit cost analysis.
particularly the history of it and how has it really influenced decision-making on infrastructure in the U.S. So I've been influenced by a lot of smart people over my career, and I've had the chance to be a decision maker myself, and I've also been someone that's been able to influence other decision makers, including meetings at the White House, testifying to Congress, briefing regional ambassadors of the State Department. So I come at this from the perspective of sometimes being involved in all three aspects of decision making. So these are my views, and this is really about where we are in the United States in relation to decision making with dams and levees. So most of my experience comes from the Corps, where I spent almost 40 years, and essentially I do the same thing now, only the decision makers and the gatekeepers are people in the corporate world. So decision making on dams has been an evolution, really. It's been erratic in its progress at times. It's been spurred by specific events and failures, and it's often connected to some larger concerns in society that are economic, social, environmental, and sometimes even political. So although those societal norms have changed over time, as a professional industry, we kind of remain the constant. So dam safety programs are organizations of trust, but too often the consumers of our advice, government leaders, owners, elected officials, see it as a promise. Through our own communications, we have allowed this misconception to persist, that safety is binary, safe or unsafe, and that safety programs can promise safety. In fact, we are managing risk, and we always have been. And so that's going to be the focus of my presentation. As dam safety professionals, we can engender trust by providing clear and compelling decisions that are risk-informed. So this is a chart of dam construction in the U.S., a little dated but illustrative. I want to connect our nation's history with the history of dams. So beginning in the last century, what you saw was a rapid industrialization in the U.S. So we're going from an agricultural society to an industrial society, and the infrastructure that was being built to support that industry. So you saw water, wastewater, roads, bridges, and railways, not many dams being constructed. In the middle of the last century, that industrialization served 2 world wars, and it also served the rapid urbanization, people moving to cities from rural areas across America. So the easy sources of clean water and power were exhausted, and dam construction began in earnest in this period. The last part of the 20th century saw the largest boom in dam construction, and then a dramatic bust. I'll focus on decision-making during this period, mostly why things happened, not what happened. So the period we're in now is different as few new dams are being built, and safety programs are evolving and focusing on fixing dams instead of building dams and looking to the future. So the last 100 years really represent a transition from benefit-cost analysis, benefit-cost ratios, to risk-informed decision-making. So if you look at that same timeline of infrastructure from a decision basis for dams and levees, you can make a few conclusions. One, decisions have never really been bad. It's always been good decisions, and two, the decision process has always been one of incremental evolution. So one period builds on the process and the lessons from the prior period. A third conclusion would be that the decision basis really reflects the societal norms of when they were made and not of today. So looking backward and judging the decisions of 50 or 100 years ago based on today's societal norms is difficult at best. And then finally, a conclusion you can reach is that science has led the evolution in decision basis. So I'm going to talk about each one of these a little more in upcoming slides, but first, what I want to talk about are the kinds of decisions we're talking about. So 3 main types. So it's a decision to act. So I'm going to call these project decisions. That is, do we build the new dam or not build it? Do we modify the existing dam or not? And so along with that goes decisions about priority and urgency of action. The second one is, once we decide to act, how do we act? So these are really design decisions. So that's the method to achieve this overall action or project we're trying to achieve. And then underlying both of those is some decision objective. So it's an objective or a goal of the project that relates to how that project becomes part of society. So this first period, pre-1920s, very few new dams being constructed, mostly meet the needs of rapid industrialization. The design decisions at this time are really just practice-based. So you see there's a lot of good work going on in science and engineering, stuff we still use today. But it's not done within the context of the professional societies we have today. So ASAE is just starting around the turn of the century. State professional engineering licensures are getting started even after that. So the practice is not yet professionalized. The project decisions are really based on where the federal government wants to put resources to support the economy and the goals of the economy, which at this time are industrialization. So there's no real underlying decision basis, it's just trust the practice. So the next period from the 20s to the 50s is this is when there's a rapid urbanization happening in the U.S. So significant increase in dam construction at this time. So you see Fort Peck Dam there. There's the main stem dams on the Columbia, Missouri, and Mississippi and Ohio are really getting started at this time. The design decisions are really coming out of some of the founding fathers of dam and levee engineering, people like Proctor Tazarki and Casagrande. You see the Corps of Engineers publishing a lot of engineering manuals, engineering regulations that have been updated and are still in use today. From a project decision standpoint, there's two big things that happened. The floods in the 20s and the floods in the 30s. Those floods caused Congress to pass flood control acts. And those flood control acts had this language that's in it. It essentially says federal resources should be invested when the benefits exceed the estimated cost. So this is really important because benefit cost analysis is not new to the country, but it's new to major civil works projects. So this is really the first time it's being used, and the underlying decision objective at this time is they should simply be greater than 1, the benefit cost ratio. So we're just saying benefits should exceed cost. Um, 1950s to 1970s, so people are now moving from urban areas into suburban areas. You see environmentalism that become a key issue. This is the peak of dam construction in the United States. It's also the heyday of standards and construction in the United States. So interestingly, there's a paper done by Bryant Robinson, Scott Shoebridge of the Corps of Engineers, where they looked at all the foundational geotechnical design criteria over the last 100 or so years, and 65% of that was done prior to 1970. So 65% of what we're using today is over 50 years old. There were some notable factors that kind of drove the initiation of some advancements in dam safety and seismic analysis, which I'll talk more about in a minute. Project decisions at this time, academia got involved in what the Corps was doing with benefit cost analysis and said, essentially, there's ways that we can improve that. So what you see here is a changing in the benefit cost analysis to consider things like discount rates and damage relationships and economic evaluation periods and consideration of future without action. So that process is getting improved. And now we're recognizing that there's uncertainty in benefit cost analysis, and that to really achieve a good rate of return on the initial investment, we want to be looking at something more than one. So there's this idea of seeking benefit cost ratios that are greater than one. I'm going to take a short detour for a personal experience that happened right at this time. So this is Governor Carter at the time debating President Ford in the 1976 election. And then you see some of the news over there to the side. That should be 1977. And it had to do with Russell Dam, which was a planned dam on the Savannah River between Georgia and South Carolina. So I'm in high school and my physics class is debating this whole issue because Governor Carter at the time was pro-environment and anti-dam. That later changed, I'll get into that. So we were debating the merits of this project. And then, kind of interesting, one thing you see here is that in the news there was a discussion of benefits of the projects, including recreation. Fast forward to today, you see that the Corps now is the largest provider of outdoor recreation in the United States, more than the Park Service, more than Disney. So it talks to our ability to estimate benefits. Then in 1976, Teton Dam failed, killing 11, causing millions in damages. And in 1977, Kelly Barnes Dam failed in Chickawa, Georgia. It killed 39 people. This is essentially in former Governor Carter's backyard. Everything changed, including societal norms on decision making. Everything flows from these two events. An executive order is passed by President Carter. He now is no longer anti-dam. The Corps begins inspecting non-federal dams. The states use those inspection results to begin building state programs. Life loss becomes a decision metric. So what we've found is legislation follows societal issues more than economic issues in the U.S. So think about 2020 being the year of $95 billion in economic loss. And to date, really nothing policy-wise, decision-wise, can come out of that. So fast forward to the 1970s, 1990s, new dam construction during this period plummets, and I'll describe. The design decisions are really, this is a lot of work being done on risk by reclamation. States are standing up programs. And designs are now standards and hazard-based, so it's the forefront of risk where we're considering different design approaches for dams that have different potential consequences. But the big thing that happens, we're still using benefit cost ratio for project decisions, but there's three new criteria to consider. One, NEPA, or the National Environmental Policy Act, is put into law, and it requires that environmental considerations are a co-equal objective of all federal decision making. Two, the National Flood Insurance Program gets started in 1968, and unintentionally and informally creates the 100-year flood as a bit of a safety standard. And then three, the Water Resources Development Act of '86 implements cost sharing for the first time. So before this, large complex projects were, their capital expense was fully funded by the federal government. Now it's 65% federal and 35% local, so it brings the issue of affordability into play. So we're not just looking at BCRs of 1.3 or greater. Now we're looking at compliance with other criteria. So this is really the beginning of multi-criteria decision making, although I don't necessarily like that term. And then the phase we're in now is really little new construction of dam. There's a lot of modifications to dam. You see all the interest and progress and design decisions related to how risk is used. Others have covered this pretty detailed. I don't need to get into it. From a project decision standpoint, benefit cost ratios are viewed as not so useful for modifications, and I think Jason Weiss with AECOM talked to this pretty clearly yesterday. So the main objectives are now to have to do with how we manage life safety risk in a cost-effective manner, and the use of TRG, which others have talked about. So I want to delve into a little bit of detail on the two key questions about benefit cost analysis and benefit cost ratios that have really influenced a lot. So the first one is, for new infrastructure projects, how good were these decisions that were based on benefit cost analysis? So here's a chart that kind of describes, or is one way to look at the issue is the current benefit cost ratios and the rate of return they describe over a lifetime since full investment. So this is a graphic out of an annual report to Congress by the Corps of Engineers having to do with flood damages. So understand that this is really representing about $250 billion in capital new project investment. So that there's a lot of data behind this. By this measure, the decision has been solid. So the initial investments are posting a rate of return of about 8 to 1. It's even greater in some systems. The reason why this has been so effective is that really the intensity and frequency of storms may be increasing, generating more damages prevented benefits. But there's also been a lot of development in the floodplain. So the benefits described by damages avoided have really increased. A key thing about this is what happens at the exceedance event for these dams and levees. So let's talk about that a minute. So here's dams and levees. They're really both formulated to deliver economic benefits up to some exceedance flows. The really only difference is that dams don't fail at exceedance and levees generally do fail. So as storms become more intense and frequent and development in the floodplain intensifies, these economic decisions look even better over time. So this economic formulation approach is one of the main reasons that return periods for spillway flow on dams and levee overtopping look similar. But it doesn't mean that the decisions have been optimized, only justified. So when I say there remains a lot of risk on the table, that is risk that's unmitigated or ignored. And I want to look at a little bit of evidence for that statement. So this is a map showing the last 15 years I was in my job in Washington, D.C. And the 4 major supplemental appropriations by Congress that were passed to deal with damages to infrastructure from flood events. So this is 4 events. They all look familiar to you. Totals about $40 billion. So actually since '89, they spent over $270 billion in disaster assistance for these kinds of appropriations. That's about $7 billion per emergency, which means the supplemental budgets exceed normal budgets for the federal agencies in virtually all years. How can this be? What this says really is we've been using supplemental appropriations to offset project and design decisions that were based on benefit cost ratios. Right, so a little more on that. This is a typical risk scatter chart or FN chart. Others have already talked about what this is. This is essentially what following benefit cost analysis decision-making with standards has resulted in 7 orders of magnitude spread in risk results. So the major findings from this are: one size of standard doesn't fit all projects, but all were strongly justified by benefit cost ratios. Design should be informed by risk. We've overinvested in some projects and underinvested in others, really without knowing. Benefit cost is leaving risk on the table. And not everything is in our control. So governance, turns out, is really important. You still seeing the slides okay? Okay, thanks. So economics have been effective at justifying projects, but not managing risk. So what else changed in relation to our decision making? Most are going to recognize this as the breach on the lower Ninth Ward of New Orleans during Hurricane Katrina. But this may not be as familiar just 15 years later. So these are the FEMA urban search and rescue markings from the flooded homes in New Orleans. 4 quadrants. The north quadrant is the date, the south are the fatalities, the west is rescue, and the east are the hazards that are present. So 1,800 people lost their lives, many due to levee failures. So just like with Kelly Bourne's dam failure in 1977, it was the life loss that spurred new approaches to safety legislation and decision making, not economic loss. There have actually been many larger economic loss events before and after this without the same impact on decision making. So as 2020 proved, our culture reacts more sharply to social impacts when compared to economic challenges. And so as civil engineers, this should resonate with us. So the economic premise of benefit cost analysis leaves us scratching our head a little bit. Why can't we extract the nation from a disaster relief environment where it's okay to invest $40 billion after events, but not enough before them? So the second question has to do with what someone mentioned on the chat a little while ago, which is why is or is benefit cost ratio a good decision metric for the built infrastructure? So not new, but the to be built or the to be modified, I should say. So I'm going to answer this in 4 slides, and essentially the answer is no. The first reason is that we transformed or imposed risk in the floodplain. So that's a trade-off that imposes a risk that's beyond the economic conditions and didn't exist before the infrastructure was built. So we fundamentally changed the decisions in the floodplain. It's a risk we impose on society for gains of the trade-off, and typically it's been done without a fair communication of that trade-off. So the second reason is that along with the chance of failure comes a likelihood of success. So the label of a 100-year flood or a 1% annual chance exceedances really means that annually you have a 1% chance of failure or a 99% chance of success. So this chart shows the cumulative likelihood of flooding over a 30-year mortgage given 3 different recurrence intervals. So the odd fact here is that this creates 2 opposing and negative realities. The first one is that because the chances of success are high, the benefits in the numerator of the benefit cost ratio are reduced to that small percentage of the annual chance exceedance. And because the costs remain in the denominator, the benefit cost ratio becomes small, in most cases less than 1. And although the chance of flooding seems small, when viewed from the life of a 30-year mortgage, they become unreasonably high. Who would build a house that had a 1 in 4 chance of being destroyed over the life of its mortgage? So the third reason is really with benefit cost analysis, we tend to overcount benefits and underestimate cost. So we're looking often multi-decade periods ahead for benefits while relying on costs that are based on maybe 10% designs. So each of these tend to inflate the actual BCR calculation. There's a lot of good reasons here that come right out of root cause analysis on cost and time growth in projects. The biggest one is we don't really understand the risk going into project decisions. So we need to better understand it. And the second one I call out is this idea of motivational bias. that motivational bias makes us think about benefits more positively and cost more negatively. And then the last reason of why benefit-cost ratios really don't work by themselves for the built infrastructure is that they ignore this concept of disproportionality. So the example here is the Ford Pinto. Of course, in the 70s, Ford Pinto was a very popular car, hundreds of thousands of them on the road, and they had a small problem, which is when they ran into collision, they tended to burst into flames. So a lot of people died and were maimed. And so on the right there, let's see if that's actually on the next slide. Nope. Let's go back. So there's a few things happen with Ford that actually follow the framework of assessment, management, and communication. They made a technical assessment that said they could move the gas tank, but it would cost $11 per recall. But that gave them a benefit-cost ratio of less than 1. Management saw that technical assessment and said it's cheaper to pay the lawsuits. And then they had to change their communication on it because their model for the Pinto was a little off target at that point. So some things can't be measured in terms of dollars, and that includes human life. So how should we make decisions with infrastructure? Einstein's advice essentially says, fall in love with the problem. So problems we really understand are more easily solved. So people talked about this. This is a modern decision focus. So it's based on a technical understanding of how things can fail and the risk associated with them. That is then used in a policy preference environment of management to make decisions and governance. And then that is in turn to allow shared responsibilities across all the parties. Sergio talked about this process a little bit. This is the federal resource process for water projects. Essentially, one, understand the problem either at the project or portfolio level. Failure modes and risk are the best way to do that. It's much better than standards by themselves. Then let risk help you classify projects to better understand their priority and urgency. Let that quantitative risk guide the development of solutions. And then use quantitative risk to then evaluate, compare, evaluate, and select alternatives that make sense. This is a really powerful use of risk in the Corps of Engineers. That part alone helped cost avoid over $7 billion while I was there. And then finally, use risk to confirm if you've actually accomplished the risk reduction sought to achieve. All right. Just a few slides, a sampling, I would say, of the lessons associated with risk-informed decision-making. So this is that same decision process, but these are some common mistakes to avoid in that decision process. So first, premature understanding of the problem. You know, we as engineers, we like to be efficient, which is doing things quicker and cheaper incrementally. But the more important thing is to be effective. So it's to get a complete understanding of the problem before we start. I would say checking your overconfidence biases regarding knowing the final solution at the beginning is a real problem. Sometimes we start out with a solution and find problems that fit it. The decision objective ends up being really important. What are you trying to achieve? So start with the end in mind. And then lastly, one of the big mistakes is letting schedule pressures drive bad decisions. So from an economic sense, it makes much more sense to spend time on the problem and the process in the beginning because it costs more later. Risk quantification is a very contentious subject about risk-informed decision-making. The first thing I'd say is everything in our world is subjective to some or even a majority degree. So let's stop avoiding subjectivity and start addressing it. It's in everything. It doesn't matter to me what kind of risk analysis you're doing, whether it's event trees or system response curves or fault trees, there's subjectivity everywhere. And the thing about the method of risk or the risk model is, I would say, don't be dogmatic or rigid in your thinking about the method to understand the problem. Event trees are great for internal erosion, but not so much for gate reliability. Fault trees are good for gate reliability, but not really helpful for internal erosion. There's a quote that says, "For rigidity of the mind, there is no known antidote. It carries the seeds of its own destruction." So that's my warning about dogmatic. And then finally, support your work with evidence. Facts, data, models, analysis, and informed judgment. The risk numbers aren't the evidence. They're just the expression of our degree of belief in the evidence. We spend years designing and building things by components, and Mother Nature doesn't really respect that. She spends 24/7 working to exploit those differences. The Challenger example illustrated this significantly. So our profession gains a better understanding of how things can fail and their consequences. We gain a better understanding of what we should do about it. The concept of potential failure mode analysis is one of the most significant advances that has led to more effective influence of decision makers. So instead of understanding how it was assembled by standards, PFMA helps us understand how infrastructure can fail. As decision makers, our relationship with uncertainty is not always healthy. What does work with decision makers in highly uncertain environments? Well, unfortunately, we tend to focus as engineers on precision, on collecting more data, on calculating a better number, and having an overconfidence in what those things mean and how effective they're going to be in influencing decisions. This is the uncertainty paradox, where we double down on what we know while we ignore that iceberg beneath the surface. What's actually effective is leveraging basic science to more cost-effectively fill those uncertainties and explain what lies beyond what we can't see. So the takeaway on this lesson is, when things are uncertain, leverage science first. So this was talked a little bit by Andy. This is the whole idea of system effects, and I'm really going to describe it with a graphic. So we've reinforced our lessons on system effects with the 2017 Orville incident. In this example, you can see on the left how single projects are often made up of multiple interdependent physical structures. And multiple projects may have interdependency within a river system. And those river systems are further part of a larger watershed. System evaluation allows us to make sense of these physical interdependencies, often via some appropriately simplified qualitative assessments, but there are good tools for at least looking at the hydrologic interdependencies quantitatively with tools like HEC1. So these lessons are now feeding into risk assessments to better consider these interdependencies, physical interdependencies. So those physical systems are made further complex with layers of human systems or human factors. And I know Dr. Irfan Alvi's on the phone, and that's great. He's one of the leaders in this field. So this includes our propensity to make errors, to maybe not have the right governance in place, to be overly influenced by political, economic, social factors associated with our projects, or even external influences at the state, federal, and national levels. For me, the biggest lesson on human factors is that they're not easily quantified, at least by engineers. So particularly putting human behavior into risk models should not be the job of engineers. But Good governance systems, like safety programs, decision processes, policies, and guidelines, are our best mitigation for these risks. And frankly, I believe those governance systems are one of the reasons our observed failure rates are not higher due to the complexity of human factors. Lessons on extreme events. I'm not sure I know of any organization that's taken to risk assessment without initially underappreciating the effect extreme events can have on risk. I know this was true in the Corps. So extreme events happen. We should all be deliberate in how we approach them from a safety perspective. This is Houston, Texas, with a geometrically accurate raindrop that fell within 48 hours. So this is something close to 60 inches during Hurricane Harvey. It's something at around, or maybe even above, the PMF. So we now have good probabilistic methods we can use within a risk framework to make decisions for events like these. And it turns out gate reliability can move our understanding of the impact of extreme events by orders of magnitude. So gate reliability is pretty important. Sergio talked a little bit about the lessons. I think Orville was instructive in a number of ways. The incident helped our industry improve by changing how we go about understanding system interactions, in particular that no-fail branches in some event trees can transition to failure in other failure modes or event trees, and that avoidance and consideration of large damage states really can affect decision-making and how risk is transferred within a system. There were a lot of really good things coming out of Oracle, and there was a lot of good things to say about the project. It really reinforced the importance of independent review and challenging of past assessments as part of our profession, and then this whole consideration of systems and human factors is really consistent with risk-informed practice, and in part, at least part of that current risk-informed practice. Decision-making at the portfolio level can be really different than that at the project level, even if the processes are based on the same risk information. That's mainly because the objectives can be different. So for portfolio analysis, we want tools that are good enough to limit false positive results, and for those tools to be internally consistent, but at some reasonable effort and cost. The reason false positives are important is because if you identify an unsafe dam as a safe dam, it can hide in your portfolio for many years. So we want to think about the portfolio as a series of queues that should be managed in an integrated fashion. So that's looking at what are you doing in dam safety studies, dam safety modifications, designs, and construction in an integrated fashion. And then one big lesson from portfolio management is that you're going to find out things and it will drive you in directions you didn't really anticipate. So that is, it'll show you where your shortcomings are in staffing and in policies, governance, and research, how you address the data. So I want to just take a second to have a final thought here. And this is a little bit dated in that 4 years ago, even the penetration of risk analysis and RIDM in the U.S. was less than it is today. Now, today, you see the 4 major federal dam owners and levee owners fully engaged in a very similar approach to decision making. So that's fantastic. We're talking about thousands of risk assessments in the U.S. But this slide just speaks to the issue of why are there still some people that want to be critical of the risk concept or talk a good game regarding the risk concept, but really don't practice it. So risk-informed decision-making is really about the practice of actually doing it. So this is a paper that I authored with a friend of mine who's one of the next speakers, Ignacio Escuder. And it really asks the question, why is it embraced in concept but not in actual practice? So I give you that to think about. I want you to think about why 2020 was a huge economic loss year that won't change our decision making. It's really about how we address also life and those consequences. And risk, as David Bowles and others mentioned, is really the way to do that. So I want to thank you. I appreciate the chance for FEMA to talk about this. The most I've ever talked about benefit cost analysis, and the most I've ever want to talk about benefit cost analysis.
All right, thank you so much for the presentation. Eric, that was very informative. I know as you talk on several topics here, the benefit cost analysis and the human factor, we have a few comments and a couple of questions. So maybe I can start with a question from, I think it's William Batty. And I'm not familiar with this, but maybe you understand it, but it says the Dutch and their water program allows for flooding and breach of levees in the form of flooders and allowing the North Sea to flood between flooders. They have assisted the Corps of Engineers after Katrina, Sandy, to extricate our U.S. system from post-disaster reactions. Why can we not move to the Dutch water system approach? Do you have any thoughts on that?
Oh yeah, I have a lot of thoughts on that. I led the U.S. government's partnership with the Dutch government for 10 years on this very topic of levee safety. So I'm extremely familiar with the Dutch and their process and their decision making, and actually consider myself quite close to them as friends. So what I'll tell you, the first thing is we're not so different than the Dutch. When the Dutch started using risk assessments, they found out that their 10,000 and 2,000 year levees were not what they thought they'd be. And when we started using it on our levee system, we found out our levee systems were more robust than we thought. So the idea of the whole government-to-government partnership was to share lessons, and I would tell you now that they are leaning towards doing risk assessments like they're done in the U.S. after some of that collaboration. As to the polders the Dutch have, 60% of the Netherlands is under sea level. But one of the main reasons they started with polders on the perimeter of their cities had to do with World War II. And so these were the areas that they would intentionally blow to flood them. And they flooded them at a depth that was not deep enough to travel in boats, but too deep to travel in tanks. And it was to protect themselves from the German invasions in Europe. So it always helps to know all the history behind some of these things.
Very good. I'm going to bring up another point here. Both you and I think I'm going to say this incorrectly. Is it Alvi? You talk about human factors, and it's very hard or can't useful to quantify in dam safety applications. And I think this is similar to the question that was asked previously. Any additional comments on that? Because I know, as you mentioned, Alvi was part of the assessment on Oroville. Because when we talk about human factors, we can talk about human factors in the design, in the assessments, and so on. But even when we start talking about response of the public, you cannot truly predict how the public is going to react in an incident event. So can you talk to?
Yeah, so I think the work Dr. Alvey is doing is really important. But here's how I see it. I think engineers getting into the business of quantifying human behavior in risk estimates is an off-ramp to a place we don't want to go. But it doesn't mean we can't sit down and go through all the human factors on our project. Let those human factors influence how we look at risk assessments and what we're estimating, where the uncertainties are, and then to line up what are the governance practices we have in place to deal with those human factors. The reality is most of our dam and levee safety programs have governance geared right towards the complexity of what the problems that human factors present. So, you know, that my takeaway from Oracle is they had a wonderful system of governance, and they used that to offset a lot of the complexity and actually make some really good decisions during the Oracle incident.
Thank you. All right. Well, thank you very much for the presentation. I'm going to stop the questions there so we can start catching up on our program. And actually, so if we have 1 minute, maybe I can give you just 1 minute on this one question from Bruce, and just another, just if you can just comment on it. You mentioned there are still numerous levee system sponsors who don't want to communicate risk to the public. What are your thoughts? Should all risk be communicated to the public or in a certain way? Or what are your thoughts?
I think if we're not communicating risk to the public, whether it's, you know, the engineer overseeing it or the stakeholder that actually has to operate and maintain the system, we're being derelict in our duties. So how can society make good decisions about what to do during events or how to develop the area behind levees if they don't understand what the risk is? So this is, so I'm not saying it's easy, it's not easy, but I've done it, and people want this, and in fact people want clear risk communication from their local officials, because that's the source of information that people trust the most. So what I would say is this is part and parcel to their job. People don't like to talk about it for this very reason. We've had about 5 decades of privatizing gains behind levees through unmitigated development and socializing the loss through things like flood insurance and supplemental appropriation. So we've got to get past this thing that's broken in the U.S. about a disconnect between what's happening behind levees and how that risk is communicated.
Thank you. Appreciate that. Well, once again, thank you very much, Eric, for your presentation, and definitely the questions. I'm sure most people are thinking about them as well, and you've opened up a little more questions from the people.
You're welcome.
We'll go ahead and move. We'll go ahead and move on to our next presentation. This is going to be done by Desmond Clifford with BC Hydro, and his presentation will be on reflecting on the past 25 years of risk-informed decision-making and looking forward to the next 25 years of probabilistic safety analysis of dams and risk-informed decision-making. Desmond, if you're ready, I'll go ahead and pass it on to you.
Well, it's a privilege to be able to speak to everybody today, particularly, in consideration of my reputation for, pointing out awkward inconsistencies, asking difficult questions, and raising issues that, create a certain amount of discomfort. So I'm very grateful to be able to do this. And I thought it would be helpful to look back primarily on BC Hydro's involvement in the development of risk-informed decision-making over the past 25 years or more. It's actually nearly 30 years by now. And look forward to where we might be going. And in order to do that, I have reflected on the full breadth of what we consider to be risk-informed decision-making, and I will be picking up on a few of the points that were made by other presenters. And I'm going to start with the some of additions to that excellent presentation by Keith Ferguson in relation to the development of risk-informed decision-making. So this retrospective look is all about looking at a reassessment of the foundational assumptions and the methods that we use for doing risk assessment, and essentially explains the various things that we've learned over the past 25 years and see where we might go in the future. And for those who aren't familiar with BC Hydro, we have 82 large dams at 40 locations in a hazardous natural environment. We have pretty well all of the natural hazards that you would want to look for in a portfolio. That is, if you want to go looking for hazards. And it includes very large dams of international, national, and regional importance. Dams that are so big that the idea of letting them fail is really not on the table. And we make continuous investments in our dams. Currently we're spending about 2 billion Canadian dollars over a 10-year period. Our overall aim is based on risk, and this aim was developed with the assistance of Mr. John Remington, who was the originator of tolerability of risk. He was the author of the tolerability of risk from nuclear power stations. To start with, I want to point out that one of the inconvenient truths, probably true to form in my case, that not everything that counts can be counted, and not everything that can be counted counts. And this is something that we need to be able to deal with the whole way through what we're doing in risk assessment. We have to start with the acceptance that whatever risk estimates we make, they're always less than they should be. And we're not necessarily focused on the right thing either. And there are similar thoughts that can be applied in cost-benefit analysis. And the extension of that, somewhat inconvenient fact is that when dams fail, real people really do get killed. We're not talking about statistical lives. This is not like a situation where you've got a meteorite and you just accept that it might happen to you, because in the case of dams, the dam's a loaded gun pointing at a known population. We're not talking about statistical lives at all. And decision makers have to take this into account. And when we transform everything to a mathematical abstraction and express it on FN curves, we lose sight of all of this, reality that's hidden behind our abstractions. And there is also the issue that copying your decision criteria from another agency, does not deal with the morally and ethically important dimensions of the whole question. The decisions imply decisions on matters of life and death, and they need to be faced. And uncertainty plagues everything that we do. We have to be honest about it. And Pete Ferguson mentioned Casa Grande. Well, we have two of Casa Grande's dams, and Casa Grande was very clear about the complexities of what we're trying to do because of how little we actually know about the materials we're dealing with. And he put it very clearly into context in relation to the fact that we use these materials that we don't really understand to create industrial artifacts that have the potential to cause more destruction than by any other peacetime activity. Now, I'm going to go at the whole question of the basis for risk-informed decision-making for dams. I'm going to pick a point in time slightly earlier than the 1997 release of the Bureau of Reclamation guidelines. And the reason I'm doing this is that in 1993, BC Hydro produced what is essentially a complete process. It was derived from documentation from the USBR and from other industries, but it included the whole question of quantitative risk criteria. There were risks to life and there were economic and financial risks, and it also brought in the notion of tolerability. And shortly after that, in 1994, ANCO produced its risk assessment guidelines. But borrowing from the UK Health and Safety Executive in 1988, now this was Mr. John Remington's work, that we transformed that into a small FN chart and we had tolerable and intolerable designations in there. The risk to an individual was 10 to the -4, and the slope of the line was -1. It worked out that that was equivalent to an expected value of 10 to the power of -3 lives per dam per year, and it had an economic risk cost of the order of $10,000 a year. Now, what that meant was that the implied value of a life was $10 million, and it also meant that if you had 50 dams, and we had approximately 50 dams in BC Hydro, as I mentioned, that the average rate of killing people would be about one person every 20 years. Now, that rephrasing of that particular criterion caused all sorts of grief, which is not surprising, but I think it's important to realize that this idea of these tolerable risk criteria were essentially moved across from the nuclear industry to the dams industry in the early 1990s. And the whole thing about event trees and decomposition analysis, sudden earthquake frequencies, empirical data, these were all covered in the guidelines that we put together, and we actually worked through the example with Stephen Bake. And the way we developed in BC Hydro, and we were in close contact with people in Australia, and it was around this time we started to work with the Bureau of Reclamation. In fact, when it came to developing the guidelines that we published in 1993, Larry Von Thun from Bureau of Reclamation was one of the panel of reviewers. We had a number of reviewers for our work in the development stage, and that included Professor Robert Whitman, who was mentioned yesterday in Keith Ferguson's talk, or the day before yesterday in Keith Ferguson's talk, and also Dr. Alan Cornell. The practice in Australia moved towards eventually production of risk assessment with their portfolio risk assessment approach, which was developed by Professor David Bowles, who we heard from on Tuesday as well, and widespread implementation and acceptance in Australia. We went a different direction. We started doing penetrating test applications of the methodology. Focus on the question, how safe is the dam, and whether or not the dam was safe enough. And we looked at a wide range of dam types, but we were always based on the premise that the accuracy and precision could not be determined. We were also in contact with Dr. Ralph Peck, who kept on reminding us about the risk of the oddball. And we had a wide range of applications ranging from spillway channel erosion, seismically induced liquefaction, debris management, failure of riprap, internal erosion, which was quantitative analysis in those days. And we reached numerical risk-based safety conclusions in all but one case. But the whole way through this, we did some blind tests. We looked at functionally simple and functionally complex dams. We looked at narrowly and broadly defined questions in a range of different contexts. And always asking for the question, as engineers do, how accurate and how precise are these estimates of the risk? But taking a closer look at the analytical foundations, because we just didn't invent all of this stuff, we can look at the whole question of judgment and model-based analysis in a framework like this, where we allow for both the empirical approach, which involves experiential knowledge, empirical knowledge, and a great deal of experience, and then reasoned explanations towards a direct judgment. One might call that an engineering judgment on the one hand, and then we can go theoretically and go through various mathematical methods to a model-based judgment, but throughout everything is underpinned by experiential knowledge. And this is experiential knowledge of the physical phenomena. And here's one thing that we were acutely aware of, because if we're applying either of these types of techniques in engineering practice. We are looking at a situation where we get feedback very quickly. We apply these methods in the construction process, and as we're building the particular structure, be it a dam, a bridge, a road, or whatever, we get feedback very quickly. We don't get feedback from our risk assessments on dams. And that's a very important thing to bear in mind. And out of this way of looking at things, we were able to put some structure around it using failure modes and effects analysis and event tree analysis to add robustness to our inferences based on empirical data and experiential knowledge. And that was, on that left-hand side is where we were in the early 90s. And then we started bringing in the types of methods on the right, covered in totality by the theory of probability. Ferguson mentioned, Casagrandi's lecture, absolutely pivotal as, Keith laid out. And he summed it up very simply in terms of 2 points: the use of imperfect knowledge, guided by judgment and experience, and this is what we do in engineering practice, and the decision of an appropriate margin of safety or degree of risk, taking into account the context of the decision. And we practice this, and this is where our engineering practice and our experiential knowledge is so important, and the professionalism involved is essential. And all of that can be built into this type of framework that I mentioned. Excuse me. Now, Casagrandi focused on probable ranges of all the pertinent quantities that enter into the solution of the problem. Things like density, shear strength, water content for geotechnical engineers, concrete strengths, concrete densities, allowable compressive strengths, on the, for structural decisions. And Pete Ferguson mentioned Professor Whitman, and we actually relied very heavily on Professor Whitman and his earlier work as we developed our capabilities. But there were a lot of other developments that underpinned everything that we did. The period from 1948 to 1974 was particularly important in a number of industries. We were able to lean on to be able to, advance the practice in dam safety. And what we were doing was we were taking experience from other industries which had been around for decades, and applying it in the context of dams. Probability, even longer. So there was a very rich, history and a very rich range of resources available to us to be able to move forward. And in economics and utility theory, the economics of civil work back to 1844, and as Eric Halpin mentioned, 1936, the Corps of Engineers were working with it. In 1973, we had the ASCE Task Committee, and in 1985, and Andy Zielinski mentioned this vitally important document by the Bureau of Reclamation Guidance to Decision Analysis. The ASCE report, raised this vexing question of the value of life, and the earliest and possibly the harshest treatment of the whole issue in relation to what market economics and willingness to pay means, willingness to pay for what, is exposed by the satirist Jonathan Swift. Now, this means that, what I'm going to put up next shouldn't be taken as reality, being satire, but it actually gets at the raw essence of the whole issue. And this is a cost-benefit approach to dealing with overpopulation in Ireland back in the 1700s. And it's quite harrowing to look at it from today's perspective, but this is the first, known use of, the concept in putting forward a policy proposal. And it's actually referred to in a lot of the foundational work on benefit cost analysis and value of statistical life. Professor Whitman's Terzaghi lecture and the curve by Becker and Whitman in the documentation of that particular lecture was referred to on Tuesday as well. Well, if we go back a little bit further, we have rather similar curves, from the WASH 1400 nuclear reactor study in 1975. And Andy Zielinski made reference to a few of the developments in the research and other areas that were progressing in the 70s. There's a few more. So everything appeared to be in place. All we needed to do was adapt the things from other industries to apply to dams. And Andy Zielinski mentioned a number of other important references. Here's a selection, by no means all, but it includes the work by Professor Bowles back as far as 1978. So all of these very important building blocks to where we got to today. Little talked about, but in my view, foundational application of the USBR's 1985 guidelines was in the state of Montana, the Tongue River Dam Risk Analysis by PRC Consultants. And Professor Bowles was involved in this as well. But this was the first direct application of the USBR guidelines, and essentially we were able to say, now how can we fill in the blanks in diagrams like these? So there was an apparently sound basis to proceed. But as I mentioned, we had spent essentially 4 years doing probing investigations. We had a number of what we believed were notable successes. 25 years on, I might be revising that opinion because every now and then our dams give us a surprise, and Professor Bowles mentioned this in his discussion the other day. But we had widespread review by eminent experts throughout the world of dams engineering. And one of the big tests was to have Dr. Ralph Peck take a very critical look at what we've been doing, and we were very pleased that Dr. Peck came back with the very supportive letter that we had gone a long way towards resolving his reservations about risk assessment in dam safety. And our relationship with Dr. Peck goes back all the way to the WAC Bennett Dam in the 1960s, and it continued right until his passing many, many years later. And as usual, Dr. Peck reminded us about the risk of the oddball, and these oddballs keep on popping up. Here's one of what we would consider our most significant successes. It was the seismically induced liquefaction of Hugh Keenley Side Dam. We did this with the assistance of Professor Alan Cornell, Dr. Bob Whitman, Dr. Bill Marcuson, Dr. Ray Seed, Dr. Peter Byrne, Professor Niels Lind. We brought in a heavyweight way of looking at it in terms of the best available expertise, and we brought it in from two different dimensions. We brought it in from the probabilistic dimension and the deterministic dimension, so we were able to create this means of getting as much experiential knowledge and dealing to the best of our ability with the risk of the oddball problem. Now, the event tree, there's a important difference between this event tree and many other event trees that you might see, because what we were actually looking at and going all the way back to Grandi's view in relation to the parameters that come into the model. Our event tree is a parametric model of the physics of the failure process. So this is the physics of liquefaction parameterized. And what we were asking the experts for was not their judgments of chance, but their engineering judgments of the probable values of the parameters that come into the solution of the problem, going right back to Casagrandi's 1963 advice. So this is the most advanced analysis that we did. It's absorbed very large amounts of money, huge site investigations to characterize everything. So you're talking into the multiple millions of dollars to be able to perform the analysis to get it to where it is. Today, if I'm asked, the only thing that I will revise would be the seismic hazard, because we've done a complete new seismic hazard there, and we would revise the consequence analysis because of development downstream. But the model in the middle has not changed. But in 1996, we had the Bennett Dam sinkhole, and that put a huge shock through the organization, and we rapidly realized that it couldn't have been predicted by either conventional analysis or risk analysis because it was due to a non-going condition in the dam. And the question was asked of me, what use is your risk analysis stuff if you can't deal with this type of problem? So everything was put under the microscope. Cruiser Lake Dam developed some sinkholes, and we did some risk analysis, but we couldn't predict the locations of the analysis, which was essential, of the locations of the problems. On the case of Cruiser Lake Dam, we did a post-risk analysis intrusive investigation. In fact, we decommissioned the dam, and it exposed how little we knew about the inside of the dam. And if you haven't performed a risk analysis and then gone and actually investigated your dam, even gone as far as decommissioning a dam to check how good your risk analysis was, I can strongly recommend that you do it. It sounds like a waste of money, but it is certainly not. We have come across this issue on a number of occasions, having done such investigations on 4 dams, which included rebuilding the upper third of one dam, rebuilding an abutment dam in another instance, building a buttress dam downstream in another instance, and as I mentioned, full decommissioning. The other thing we realized was that there were some problems that could not be solved with contemporary risk analysis methods, and they're the type of problem that Andy Zielinski mentioned in his discussion. So 25 years ago, we knew that there were many things that we would need to improve on to be able to deal with some of these issues in relation to the risk of the oddball. We also determined that the quantitative risk criteria did not present a sufficiently holistic way for safety decision making, and we needed a better understanding of the science and theoretical underpinnings of risk analysis applied to dams because of this vexing problem of uncertainty that Dr. Casagrande pointed out. Your as-built drawings do not necessarily reflect what's in the body of the dam. So one of the big efforts in the the late 90s, early 2000s was to put some scientific and theoretical principles in place in this particular domain of risk assessment in dam safety, and we focused on risk analysis, and that was a major effort, where Professor Greg Becker and I, supported by Carl Dyson, the Bureau of Reclamation, and Andy Zielinski in Ontario Power, with financial support largely from the hydro industry in Canada. We had great support from Sweden, and we had great support from the Bureau of Reclamation and Corps of Engineers. And the late Gary Salmon coordinated the development of the book. That, though, was a 7-year effort to get that documented. So based on those experiences, we moved into a risk-informed decision-making mode where we perform essentially, as a matter of course, the qualitative analysis first. We put much sharper focus on vulnerabilities. Now, vulnerabilities are directly connected to failure modes, but we also shifted to the notion of functional failure mode, the whole question of loss of function. So what function does this component provide? What can we do to make sure that we achieve it? And we use this concept of vulnerability, which we can then use to mimic probability of failure based on parts count method, establish norms of good practice and engineering principles. We can take account of redundancy and risk control measures, and we scale it to frequency of demand. And we can mimic the probabilistic equation without actually having probabilities of failure, because if you talk about probabilities of failure, in a lot of the public discussions, things get rather difficult very quickly, whereas what you're really trying to do is focus on making your dam safer. So we've been able to, use vulnerability in a way that allows us to drive home, in terms of our risk reduction process in an effective way over the past 20 years. One of the other important things about it is that the process is amenable to empirical validation and control. We get feedback, and that is vitally important in terms of being able to demonstrate confidence in what we're doing. And when it comes to limitations of our knowledge, we just have to learn to live with them, but deal with them in an open and transparent way. And one of the important things, and Eric Halpin mentioned about don't get hung up on your risk analysis method. I absolutely agree, because there's no such thing as a perfect one-size-fits-all. This is superior to all others. That doesn't exist. The wish for it is very strong. It won't die, but it's just not going to happen for a wide range of reasons. So there are many aspects that, as Andy Zielinski said, you cannot solve with particular methods. So each method has its advantages and its shortcomings, which we have to understand. And the best way to deal with all of this is, just recourse to a, dispassionate, annotated compendium of techniques that can help guide the selection, and the professional must take responsible for choosing the method and demonstrating that the method is fit for purpose. I thought it'd be useful to show some, the obvious limitations of some of the established methods that we brought in from other industries, to be able to demonstrate that not everything was perfect when we started off with, and that we have still got room for improvement. When it comes to dealing with this question of complexity, and this is where I want to get back to Casagrandi's most important observations, is that things like multi-level failure modes and effects analysis, which is virtually the same thing as potential failure modes analysis, and failure modes and effects analysis are suitable for certain types of problems. But as the physical complexity increases and the functional complexity increases, and Eric Halpin mentioned fault tree analysis for gates, so you're getting into more complex areas, so you've got to go for other methods. But there's a whole area of complexity that Andy Zielinski was alluding to, and even describing to some degree, that aren't covered by these methods, and that we will need new methods to deal with it. And one of those is this problem of unusual combinations of usual conditions. Professor Bowles mentioned this the other day, and as I mentioned, we identified this problem as far back as 1996-97. It took best part of 10 years to raise the funding to be able to do something about it. It took a few more years to get everybody together, and then it took 7 years of concerted effort to get the work done. And we're faced with the problem that the probability of demand is not necessarily equal to the probability of the extreme events summed up. And this is a very important fact. And Andy Zielinski provided a very useful diagram that shows this question of the pool level, the way things change in time, and the difficulty of creating this type of model in an event tree. But that shouldn't have come as a surprise to us because it was all laid out in the fault tree handbook in the nuclear industry back in 1981. And then, you get into this problem that, how do you capture all of the sequences? And this gets into the problem of winning the lottery, because we're faced with the situation that these, unusual combinations of usual conditions might have vanishingly low probabilities. In the old days, we used to screen out failure modes under the guise of judicious pruning of the event tree to avoid the bushy mess. In the modern context, it's not such a good idea to screen anything out, because there's no logical way to differentiate between the credible and the incredible accidents using probability. And this is the problem, that all probabilities are possibilities, no matter how low they are. Another thing that we moved to was shift the focus from failure modes to functional modes, and to focus on components and the understanding of how the dam might work. I'm going to quickly show, here's a diagram, simple schematic diagram, spillway gate, simple model. Each component has at least one functional mode, and we can derive the failure modes directly, and we can create a functional analysis diagram of how it works. Hugely informative and understandable by anybody. And then when we add in our systems and operational factors, our diagram of how the system works gets a bit more complicated. And before long, for a very simple two-gate system, we end up with something like a relational diagram that's something like this. There's no starting point, no ending point. Everything functions through time, and if the dam fails, well, that's your end point, but you have to get the thing to overtopping or some other condition before you get there. Otherwise, it's a continuous process, hence the need to look at continuous in time. And this is the book that came out of all of our work in relation to how to deal with this problem. Andy Zielinski mentioned it earlier, and he also gave a very useful example of how things can go. Now, as you'll see from this diagram, I've pushed up and changed some of the words compared with the earlier one, but there's a gap in the middle to be filled in, because I don't think, as Andy suggested, that, we're anything close to the end of the journey. And I mentioned this problem with the, vanishingly small probabilities. They happen so regularly, as I mentioned, winning the lottery. And as Professor Bowles suggested the other day, these things about failures, the more you get involved in risk analysis, the more of them you do, the closer you are to having the experience of a failure. And that will give you experiential knowledge, but it won't be very pleasant. Some quick notes on tolerability of risk and alarm. I mentioned that we'd worked closely with Mr. John Remington, who was the architect of the process back in the 1980s. And his advice is that, in principle, tolerability of risk approach is less suited to dams and dams and bridges because of their long life expectancy. And his advice is to essentially make it as safe as you can at the start, and then not allow it to deteriorate. And that gives you a different interpretation of a LARP. And Keith Ferguson mentioned the need to look at, a LARP in more detail. Because for a system like a dam or a bridge, any of the heavy civil structures, you're talking about using a LARP to maintain an already low level of risk. You go in for a very low level of risk to start with, and then you keep it there. So a LARP is all about keeping the risk right down at the bottom of the triangle. There is a spectrum of applications for a LARP. On the left, the LARP process holding an existing level of risk very low. In nuclear power stations, in the view of John Remington, they are malleable. They are amenable to further improvements in safety as technology advances. So that was the premise for 1988's tolerability of risk. And then reducing risk, protecting people, which a lot of people refer to as a source for information risk-informed decision-making, rely on the whole notion that in industrial safety, you can continually improve risk. And the whole idea that risk isn't being continually improved really doesn't fly. We see it in automotive industry, we see it in aircraft, we see it in healthcare. Risk is always being reduced. But it doesn't get us around the fact that there will always be some residual risk, and residual risk is not something that you're going to be too happy about, but you have to live with it. So I usually refer to somewhere on the undesirability scale. There's nothing desirable about a risk unless you've got a benefit with it, and even when you do get a benefit, the risk is always disconcerting. And one of the things that we learned from John Remington is the role of what is technically possible, what is good practice, and what is the cost in money and trouble of doing better. But in his view, good practice is the minimum requirement. And he also recognized there are a lot of situations that are not covered by accepted standards. Finally, I want to talk about where I see things moving into the future and being able to capture on the ever-increasing power of computers. And the whole thing about computational dynamics allows us to look at this emerging domain of phenomenology, where in the same model we can bring together the spatial issues, and we can do this with 3D GIS models, temporal issues with system dynamics, the mechanics of the whole thing, bring in the physics, and the complexity of the way things work. Like if you look at a micro level at how complex the motion of water through the pores of the soil into a crack in a foundation are, you've got very complex, geometric problem to solve. But the domain of topology allows us to deal with the all of these discontinuities and variabilities in a more consistent way within a computational model. So I'm looking at computational risk analysis as a means for being able to essentially address a lot of these problems that, going back to Casagrandi's insights indicated that to be able to really do a good job on risk analysis for dam safety, we need to be able to deal with the complexity of the materials that we're working with, what it looks like inside, and I see the computing power that is becoming available. Now, presently, you can only do these types of models on, in a quantum computing world or on a supercomputer. You need massive computing time to be able to do it at the moment, and the amount of power involved is certainly beyond what we have on PCs. But I tend not to worry about that, because what we find is that the computing power becomes more and more accessible every year. So some brief conclusions. At a macro level, which is where we are often building our models, the function of a dam is phenomenologically straightforward. Like, you probably can't get anything simpler than a phenomenological model of how a concrete dam on a rock foundation works. But the key is physical and functional in understanding these things, and we have to realize that dams are unique structures. And it's the unique structures that has the micro-level behavior causing the problems that we revealed with our various investigations into dams that we've done risk analysis on. And there are complex interactions between the water and the materials in the dam and the foundations and abutment. If we can represent the failure mechanism in a straightforward way, we seem to get reasonably results at a macro level. But there are some things where things are going on at the micro level, and internal erosion is one of them, that can produce significant surprises. And there's no transparent way to answer these questions at the moment. And as Andy Zielinski mentioned, the linear chain of events can only capture a small number of the issues. And this whole question of these unusual combinations of usual conditions and how to do a better job of them has become extremely important. So inside and outside our industry, as Andy mentioned, things have moved forward. And Keith Ferguson pointed out some areas where we need to move. And one of the problems with safety is a dynamic non-event, like reliability. And we can't measure it directly. And this is perfectly clear from reliability data. We actually characterize reliability in terms of unreliability. And we often assume that safe is equal to 1 minus risk, but that's only one of the interpretations. There are many interpretations of a lot of the terms that we use, which we're going to have to be very careful about. So if safety is a matter of perspective, then the whole way the risk is used is a matter of perspective as well. And Andy Zielinski mentioned progress, along the same, lines, best has a short shelf life, tend not to use it too much, but good can last a very long time. And we should not, forget the awkward fact that our risk estimates are abstractions, but when accidents happen, real people really do die, and decision makers need to understand this, thereby bringing in the need to consider the moral and ethical dimensions of tolerability risk in our thinking. Thank you.
Thank you very much, Deb. Very informative, good reflection of the path and kind of connectedness to Ferguson's presentation. I like your comment about functional risk analysis, and I think those are some ways that we can really look at the whole system, and so I think that's really good to look at future progress in that field. We do have a question here from Dr. Alvey, and it says, given the issues with empirical validation and potential for surprises, which you mentioned, could you comment further on the limitations of dam risk analysis methods? I don't know if you can see the question.
Well, the whole question about empirical validation is extremely important. And as I mentioned, I came from a world whereby we were building things. I was making predictions, getting myself at loggerheads with the client about cost overruns and everything else. But whether or not my predictions were correct became perfectly obvious very quickly in the construction process. So I was getting lots of feedback, and I become calibrated. What we can't do is calibrate probability. Two people can come up with, we're given exactly the same data, and come up with the same value of come up with different values of probability. One might say 10 to minus 1, one might say 10 to minus 4, and neither can be proved to be wrong. And that brings a problem of what do you do about it? So my way for having some type of empirical control is to do the analysis and then go and do some investigations into finding out what is really going on within the body of the dam, obviously keeping away from the core, but to go and see have we got ourselves a reasonable representation of what exists in the ground? That then gives us feedback, which we can then use. But without feedback, we don't actually know. And you can't, having participated in many, many risk analyses does not mean that I'm expert on risk analysis. I need the phenomenological understanding to be able to make any claims whatsoever that I'm reasonably well calibrated. So it gets back to the whole question of calibration and validation.
Thank you very much. I think that's a very good answer to that. We will go ahead and thank you for the presentation. So move to the next presentation here. Appreciate your insight, and I'm sure if people have more questions, they can post them in the chat here. Our next presenter is Ignacio from Universidad Politécnica de Valencia.
Thank you very much for counting on me for this interesting course. And I guess after 3 days, there is no much room to surprise the audience, but I'm going to try to at least sound interesting. Let me show you what I'm going to talk about. After a short introduction, we will talk basically about the use of risk indicators for prioritizing dam safety investments. Then we will talk about the issue of not only climate change, but other time-dependent issues. I will bring some practical international examples, and I will make some final remarks. On the introduction, this is a little bit about me. Some of you might have seen this before, though the years keep going ahead. I was born in 1971, and by that time, almost a non-scientific journal in civil engineering, nobody was talking about risk. It was me being born, and everybody was starting to talk about risk. And in the meantime, I did my bachelor and master at UPV in Valencia, and then at Wisconsin University. Then I became a professor. I created a company called iPresas, and I've been for a long period linked to different positions in ICOL, and now I'm the president of SPANCOL. And in the meantime, which is basically what I was trying to show here, the number, as quoted by Bakker and Christian, the number of times risk is highlighted as a keyword in any scientific journal is just going to the infinite. So a little bit of perspective, the issue of dams is that they very much, among other things, they very much interact with natural hazards. Here you have a graph on how United Nations classified natural hazards, and we are mostly related to floods and earthquakes, but not only. In any case, if we want to talk the language of the United Nations, this is how they characterize natural risks in terms of average life loss. So this is like the multi-hazard, multi-risk map by the United Nations, and they update data and results every 10 years. So this is the latest available. So this is the language that is spoken when talking about risk at the United Nations. When we go a little deeper in the meaning of or the numbers that populate that average annual losses, then we have people affected, damaged, and people killed. And numbers are impressive every decade. That has also made other international players, like the multilateral banks, to make a step forward in not only understanding but conceptualizing and applying risk analysis to their civil projects. One example is the Inter-American Development Bank. In just 12 years, they came from a very high-level policy to a very detailed 5-step risk analysis procedure to be applied to basically all their portfolio of civil infrastructures, and not only, of course, to dams. If we get a little bit more into the dam sector, and you are probably most of you familiar with this publication from the World Bank, very recent, in which we are talking about many of, they kind of compile the practice on many of the issues you've been talking about in this course. Individual risk, societal risk, ALAR principles, and risk indicators. Risk indicators as a way to inform how to prioritize investments. And particularly one of the risk indicators the World Bank captures in this very recent publication was firstly captured by SPANCOL, the Spanish National Committee on Large Dams, based in some experiences at the Douro River Basin, and it's the so-called equity-weighted ACSLS. I'm sure you've talked before in this course about ACSLS, and the equity-weighted part of the acronym just incorporates one more issue, which is how far are you from I don't want to say tolerable, but a reasonable probability, reasonably low probability of failure, and that incorporates then in one only indicator basically societal efficiency, economic efficiency, and equity altogether, not necessarily prescribing the weight of each of them. So this is the introduction that led me to present you risk indicators in a big picture. And now let's see how we use them for prioritizing dam investments and what is the theory behind. Let me show you a number of journal papers where you can get deeper on these, particularly for the younger audience. There's a couple of papers in Structural and Infrastructure Engineering journal on the suitability of risk reduction indicators to inform dam safety management, and particularly with the focus on the new risk reduction indicator on the equity-weighted ACSLS that can provide you with full background information. So basically that's the formula. There's a number of indicators almost everywhere, but as I mentioned, it's this particular that I wanted to focus for a while. It's on balancing what we know about ACSLS with how far are you from a reasonably low probability of failure, and then use it on portfolios where many decisions have to be made over the time. Then imagine if you had all your risk estimates by any type of model, and you have your risk actions, and you have a large portfolio and a number of actions to be implemented. And if you could nicely use these indicators to give you, to put you some light in the tunnel of what to do first and later, and if it would make sense or not. So, see to the right first. The left is, for instance, how you can use it. But if you see first to the right, that doesn't mean anything because it's an aggregated value of risk, but it shows you very well the path. If you have a large portfolio, this case was 27 dams and more than 90 investments to be made, and you don't systematically use any kind of risk indicator, if you are lucky, because this is done with 1,000 simulations, if you are lucky, you will be moving through the average random path. If you're a little unlucky, you will be closer to the worst, and if you are a little lucky, you will be closer to the optimum. And that's how it looks if nobody is driving the car in a figurative sense. So, if we use risk indicators, we can do nice things like this. For instance, imagine it's not that you are renouncing to any of the investments, but you are just evaluating the path. So imagine the starting point and the end point are fixed. And of course, the more concave your path is, your curve is, the better you are doing. So you can, for instance, use just the simple formula as comparing the two areas that I put in the graph, and then you can, for a particular sequence of investments, compare how different indicators are performing. As expected, the cost, it counts for the three aspects. Equity weighted is not the best performing, either in social, economic, or equity, but is the better balance in the three columns. That can get more complicated, and I have no time to get too much into details, but let me introduce three papers that might be of the interest, particularly of the younger audience. If you are concerned about how it applies to system of dams, there's a journal, there's a paper on the Journal of Risk Analysis that can give you some clues on how to operate that on system of dams, either if they are in cascade or not. In the interaction with other infrastructures as levees and total risk or non-breach risk, there's another paper that can give you interesting insights on how is that sequence, let's say, resistant to the uncertainty, or how robust is in the presence of uncertainty, can also be taken into account. And that's the third paper that I have in the presentation, just inviting you to download them and read them. There's one very last issue that I wanted to touch, which is also that we don't want to have a fully static picture of today, particularly in the context of climate change, and there might be other time-dependent issues. For that, we have just finalized a couple of works, and we have, again, sorry to overload you with all these papers, but I think it's interesting, as I said, in particular for younger attendees, to download all of them and have a look to them. And in these latest about how to incorporate climate change and time-dependent issues like big movements in the population downstream, etc., into the formula, if you want to name it like that, of prioritizing investments, there's things that can be done for analyzing how well your sequence or your path is adapting to what the future looks like. And for instance, there you have the sequence on how can you handle it. And certainly you will need to do something that allows you to judge a period of time. And you can use, for instance, another indicator which we have named under accumulate ACSLS, in which you will be able to make the same type of judgments I was making before over time. It looks a little bit like this. No? It's putting another variable into our minds, though unfortunately our minds like to be don't like to be thinking on time. It's okay, I'm doing one thing and another and changing my portfolio, but time goes by and things change and the risk profile is changing while I'm acting. And then we have, this is very similar to what the type of graphs you get in a normal cost-benefit analysis. But then you have to be accepting to be doing numbers like this, accounting for the benefits, but with a different picture of the evolution of risk over the years. That will end up with graphs and discussions that will look like this. This is a case for a Spanish dam. And then you can, on one hand, you can be checking the influence of your time-dependent lack of knowledge in your overall risk estimates and results. Or if you wish, after you have processed it, and if you want to check it against one of the tolerability guidelines, you could be looking on how your estimates are moving over time. And when you translate that into your sequence, that will make change. There will be sequences of actions that will be less changeable because of the time-dependent issues. Some cases of application. I have a number of cases. I have selected just 3 or 4 very fast. And there's cases in a number of continents. I wanted to reflect to a word that Eric Halpin said before about not being dogmatic. When you work in different countries, under different contexts, and with different systems, that's really a key thing. Be able to adapt and just to make whatever fits better in each case. That was the first example that I had put before, and this is the example of the Duero River Authority, where we started 15 years ago doing this type of simulations and numbers, and you can see the curve was nicely concave in the sequence of investments that we end up advising. This is an example in Sweden, and there's a number of actions, as some of them are easier than others, some of them are more non-structural, and like improving the warning system, but the others on gate reliability, another on even constructing a new diaphragm wall. And that's how it looks like when you use risk indicators to show the impact, the relative impact of the sequence on risk. In some cases, certainly for some recommendations, there's no data enough, or you want to say there's too much uncertainty. And also the indicators can help you to identify no regret decisions and where to start, regardless where you are. You might be an order of magnitude higher or lower, but in some cases, you have to start by emergency action planning. And if there's a need of a major new spillway, certainly you will need more data in some cases to make that decision defensible. This is a case in Albania a number of years ago. Other portfolio in Spain, final results only. When you apply systematically this way of thinking, you end up with action plans. You can show the ideal order of every action, and you can show what is in green, what is in yellow, what is waiting, and why, and you can monitor what is the action that you are getting done. There's, as I mentioned, there's all type of examples, and in this case, and just because I'm talking so much about numbers, I wanted to put this picture with this in Tegucigalpa, Honduras, where the accounting for the local knowledge and the experience they had with Mitch and other hurricanes, and allowed us to certainly enrich the numbers supporting the estimates, and then the indicators are more robust. The other thing I think it's important not to forget is the non-breach risk, or the total risk. This is a dam in close by Montevideo in Uruguay, and there's a very nice problem, at least from the theoretical point of view, which is, okay, if I decrease my failure risk, I might be increasing the total risk. In this particular case, because there is water treatment plant serving 2 million people that can be flooded if you get your dam safer from a hydrological point of view. That also can be captured, the case can be made, and one of the results of this work is that it finally made the case for a redundant water treatment plant, and another dam in another basin is being built for that large community of 2 million people. Even in the cases where we are doing only type of screening, I don't like the word screening, by the way. This is a little bit more than screening, because you put a lot of knowledge and relative judgment on it. For, as I say, for no regret actions, for instance, identifying in a large portfolio where emergency action plan is more critical, or where new instrumentation is critically needed, you might apply also some sort of indicators, even if they are not highly sophisticated quantitative numbers. You can show the paths. I don't want to use all my time without allowing for discussion, so this is a case in India, and in some cases you have to really account for uncertainty and have a kind of two different routes, if you allow me to use that. One which is where you basically okay with with a sequence of investments, but another where you really want to wait to have a little bit less of uncertainty, as I had mentioned before, for other cases. Last but not least, this is another international example, Cerros Colorados in Argentina. It's a super complex system, including a natural lake as site. And it's a kind of a 3-dam system plus a natural lake that is a site, and dependently on how it reaches, you can have a combination of the very difficult type of failure modes. But by accounting, by putting some accountability on this and making the numbers and showing the numbers, in this particular case, there was a big opportunity because there is a dam under design upstream, which was only going to be, conceptually it's only for hydropower, but with some adjustments, it can provide the hydrological safety that this system needs while maximizing the let's say, the added value for the society, with not certainly a big increment in budget. So final remarks. In the operation, sorry, I'm missing something there. In the operation, certainly risk indicators allow you to get more efficient. In the design, and this is a topic I couldn't touch because I didn't have that much time, in the design, risk indicators might allow you to find close by the optimum rehab designs. In feasibility phases, like in the Argentina examples, incorporating all these capacities on cost-benefit analysis or sort of cost-benefit analysis and risk indicators might make projects be really understood as more beneficial. The case of a new dam that could be beneficial from hydropower perspective, but if you account for the flood protection benefits, it becomes much more beneficial, and that can be made very clear. Finally, this has to be done in practice. You have to learn, you have to investigate, you have to understand your limits, what you can do and what you cannot do, and you have to go through what Eric and myself call a full cycle to success in our paper of 2016, in which you have to go all the way from the ontology to what we call the forgotten, and the final result is decisions, and decisions are to be made. Thank you very much, and I think I made it on time, and thank you very much again for all of you, the attendees, and the friends that I had the opportunity to meet today here.
Thank you very much, Professor. Appreciate your presentation here, giving us additional international perspective. This was very good. I don't see questions in the chat right now, but we'll probably have some later. We'll continue watching the chat when we're done. With that, we are supposed to be going to break right now, during which we'll show, I believe it's the second part of the Oroville Dam Comprehensive Needs Assessment.
Had already started working on risk-informed decision-making processes and procedures. So we went ahead and adopted what they had prepared and built upon that. One of the things that we did was expanded the matrix, and I'll show that a little later, to meet the needs of a dam safety project. We also use semi-quantitative risk analyses for the various potential failure modes to establish a baseline or the existing conditions. So these two efforts were the L2RA and the CNA. There were basically parallel efforts, but they were independent from one another. The L2RA team and their subject matter experts did their risk estimates, and likewise the CNA project team did their own risk estimates. Lastly, our CNA measures are equivalent to risk treatments that are commonly known in the risk arena. This is a slide of the matrix that was used for the project. So these the O&M risk matrix, it's kind of outlined here in blue. You can barely tell the dash line. So what we did, we in essence expanded that matrix by 4 rows and 4 columns. And what we did is superimpose the commonly known FN chart and also plotted the tolerable risk lines that are part of those FN charts. So this is the matrix that we use for the project. And one of the things that we wanted to do is have something that the department could, when they did their risk evaluations, not only for dams, but other state water project facilities, we wanted a single location where risk would be plotted when it came to prioritizing projects in the future. So, as I mentioned before, we started off with 171 potential failure modes. That number went up, and through screening and combining and eliminating the failure modes, we ended up with 129 failure modes. The thing that we did when it came to consequence categories, we did not only look at life loss, we looked at, in addition to life loss, we looked at regulatory compliance, we looked at flexibility and reliability of water deliveries. We looked at flexibility and reliability of other state water project purposes, and financial impacts. At the bottom of this chart or this matrix, we only show two consequence categories: public safety and financial impacts, because those ended up really driving other risk. So all in all, or before I go there, one of the other things that we did, we also looked at 3 to 4 different scenarios. So again, we didn't not only look at failure of the facility, but we also looked at heavy damage, light damage, and no damage. So all in all, we ended up evaluating over 2,000 or performing over 2,000 evaluations. After all that work, and what was shown on this plot is the highest risk for any given failure mode. As we could see on this chart, 54 of the 129 are considered to be negligible, which is approximately 42% of them. The complex is pretty good. As I mentioned before, the L2RA did their own evaluations. For the most part, they only looked at life loss or total failure of a facility. They did evaluate more failure modes than the CNA project, but at the same time, they consider a higher number of those failure modes to be negligible, which is approximately 59% of the failure modes from the L2RA they consider negligible. Moving on to the measures. So the various task teams, they, through a series of workshops, did some brainstorming to identify measures that they thought would be good for reducing risk of the existing conditions. These measures were subsequently screened. There were a number of them that were either studies or instrumentation related. Those were handed over to the Task 6 team. So they were in charge of studies, of recommending future studies or instrumentation. And then what remained, they eliminated those measures that were inferior. Once they completed all their screenings of measures, those were passed on to the project team for the plan formulations. So this matrix identifies or shows what failure modes were addressed by the measures that were passed on to the project team. So 31 of the failure modes basically were or have a measure that addresses them. So then when moving on to plan formulation, early on, the IRB made a recommendation to the team, and that was when you start formulating your alternative plans, you should consider formulating them based on themes. So we definitely did that. Next, we considered a mixture of the different measures and compatible combinations. We built the plans that met the objectives and constraints that were identified early on. And then we refined those plans as more information became available. So when it came to scoring and what criteria we were going to use, we basically looked at what could be done to reduce the risk and residual risk. We wanted to make sure that it promoted resiliency, using the Corps of Engineers Engineering and Construction Bulletin that includes, prepare, absorb, recover, and adapt. And, we also wanted to use the best engineering practices. We did not want to recommend or include a measure that would be risky or it was just not good engineering. So after a series of workshops with the project team, we ended up coming up with a total of 10 plans. For the most part, let me step back. All plans have 5 measures that are common to all of them. So what's highlighted or shown here in blue and these other 2 items are in every single plan. Plan 1 basically has the most measures, and it includes high-level outlet, and in addition, it also includes a low-level outlet. The difference between Plan 1 and Plan 2 is that the low-level outlet is at elevation 435, and Plan 2 does not include a high-level outlet. Now, when we look at the bottom for the total weighted benefit, Plan 1 is actually lower from the simple standpoint that the team or the group believe that the risk associated with constructing a low-level outlet at elevation 340 were much greater than the others. So moving on to the findings. All of the risk estimates made by the CNA team fell at or below the tolerable risk line. No acceptable risks were identified. So as a result of that, no dam safety issues were identified that exhibited a need for immediate risk reduction. And this finding is consistent with the use of tolerable risk guidelines that are used by federal agencies with large portfolio of dams and safety dam programs that are guided by risk-based approaches. So the department, in addition to Oroville Dam, owns and operates numerous other dams. So we felt that our results here were in line with what other federal agencies use. There are a handful of PFMs that require additional analysis. One of them being the flood control outlet structure. Now, that structure, as we were going through the CNA, there was a structural analysis being conducted or performed for that facility. We are anticipating the final report to be completed here in February or March at the latest. Another failure mode that needs, or we recommend that additional exploratory work be performed is the contact point between the embankment and the concrete monolith. There's potential for seepage at that contact, so one of our recommendations is to do some exploratory work there. Now, this work, it's all based on semi-quantitative risk analysis. So some PFMs could actually be an order of magnitude higher or lower as a result of that. So there were a number of recommendations that were made by the CNA team. I'm only going to highlight two of them. The first one has to do with the portfolio of projects. Our recommendation is that the department do a risk assessment at other critical state water project facilities to better understand all the risk, and so we're going to need to read through this one. So as I stated before, the department owns and operates other critical facilities for the State Water Project. And in order to better understand the risks that are associated with the Oroville complex relative to the other facilities, a risk analysis would need to take place or be performed. And after that work is completed, we would be able to prioritize projects accordingly. The other recommendation has to do with the work being a semi-quantitative risk analysis. Our recommendation is that a feasibility study and a quantitative risk analysis be conducted before any of the plans are implemented to ensure that dam safety needs are truly present and require such projects. However, there are individual measures that could be treated or projects could be led so that facilities can be further improved. And we did make 3 recommendations that measures be implemented. One is for one of the.
Good afternoon once again. We will continue with our program. We have 2 more presentations for today. The first one is going to be by John France with JWR Consulting, and it'll be titled Risk Analysis is Fundamentally Changing the Landscape of Dam Safety in the United States. And then after that, we'll have Sean Askelson, Chief of Hydraulics and Hydrology Branch with the U.S. Army Corps of Engineers, and his presentation will be on Detroit Spillway Gate Rehabilitation Pre- and Post-Fire Hydrologic Risks to Construction. Go ahead.
Good day, everyone. Glad to talk to you today and sort of offer a perspective. For those of you who don't know me, I've been practicing in this field for a bit over 45 years now. So about half of my practice was before we really started to integrate risk analysis and risk-informed decision-making into dam safety, and about half since then. So going to just offer some thoughts of sort of my perspective on how risk and risk-informed decision-making is really changing the way we do dam safety work in the United States, and I think mostly in good ways. You've certainly heard there are issues that we need to deal with. There are some debates we have amongst ourselves about how we do this, but I think the introduction of considerations of risk into our decision processes has really benefited the profession and dam safety as a whole in the U.S. So I'm going to talk a bit about the risk approach compared to deterministic methods. David Bowles talked about that a little bit. I'm going to expand that just a shade. Then talk about current risk, but only briefly because you've heard a lot about who's using risk and how it's being used. Talk about a couple examples and then close out by offering some of my thoughts on how this has really been changing the way we do practice in dam safety. So beginning with the deterministic approach versus risk, the risk equation, you've all seen that before. I'm not going to belabor it. The probability of the load times the probability of some adverse response given that load times the probability of a consequence, usually in terms of life loss. The thing that's really significant about that, I think, compared to deterministic methods is the explicit consideration of consequences, which deterministic methods previously just did not do. That was not something that was explicit in our consideration. It was implicit in factors of safety and design criteria, but consequences did not explicitly enter into the consideration. Risk calculations then are being used currently against these guidelines, and the example I have here are the reclamation guidelines. And reclamation expressly does not use the term tolerable risk guidelines. The Corps and FERC have been using that. Others have used that. I think there's some good discussion and debate that could be had in the profession regarding the appropriateness of technical, of tolerable guidelines. Tolerable to whom? These have been really developed a lot as agency guidelines by agencies that are self-regulated. And to my view, there really hasn't been a lot of vetting within the public or within governmental entities outside of the technical agencies of how tolerable are those. So I think that's worth considering. And also some discussion, as has been mentioned earlier, about how ALARP, as low as reasonably practicable, lays over this. That once we get a dam below the tolerable risk guidelines, are we done? Or do we need to keep thinking about it and looking at it in terms of ALARP and, as was mentioned in earlier presentation, to use ALARP to push to even more safe structures after we've reached these guidelines? Go back and think about deterministic methods in the day when we were doing things deterministically. How did we do that? We basically had a number of things that we would calculate, and we felt comfortable as engineers because we could calculate them, and that's what we like to do. We had a spillway capacity, and we could compare that to some inflow design flow. And we could compare how a structure would perform from our analytical calculations against a designated earthquake. We could calculate stability factors of safety. We could calculate stresses in concrete structures. And those were all good, but some things we really didn't have good hard factors of safety or calculable numbers. An example is subjective judgments about observed seepage, and is that seepage significant? Is it a concern? So we did all of those sort of things and put them together, and that's how we would analyze dams and decide whether we thought that they were in good condition or not. There are some shortcomings to that, in my view. One, there are variations in inflow, flood, and earthquake criteria among different organizations. Some would design for a 10,000-year flood, or a half a PMF, or a PMF, and some for a third PMF. And earthquakes similarly would have some inconsistencies. Factors of safety mean different things, as I'll demonstrate here shortly. Not all factors of safety are created equal. Regarding seepage, there are variations in subjective judgments about seepage. Some people might think seepage was quite serious. Another engineer might look at it and not do that. So there were inconsistencies there. And certainly a lack of explicit consideration of consequences. And an inability or difficulty addressing risk related to things that didn't align themselves with calculations of numbers, like operational issues and non-standard failure modes. So inflow, flood, and earthquake criteria. Think about that for a minute. Inflow, flood design and earthquake criteria varied among different regulatory jurisdictions. Take a look at a probable maximum flood, a common deterministic criterion. When we've looked at those now in terms of risk and in terms of recurrence intervals or annual probabilities, we find probable maximum floods in different locations may be orders of magnitude different in likelihood occurrence, and similar for maximum credible earthquakes. So this really results in an inconsistency with the deterministic methods by applying things like probable maximum flood and maximum credible earthquake. Factors of safety. I think factors of safety can give a perception among the public and perhaps even among some engineers that a design meeting a recommended factor of safety must be safe. That is, there's no risk. The probability of risk is zero. We know that's really not true. It's far from true. We can't design a structure that has a factor that has a zero risk. So factors of safety with same calculated value are not all the same, and I'll illustrate that a little bit with the next few slides. If we think about uncertainty and how it plays in, and let's think about soil shear strength in calculating a factor of safety for an embankment dam. Well, there's uncertainty on that shear strength as represented in the plot at the right. There's a mean, but there's a distribution on that shear strength of likelihood of it exceeding a particular value. If we then calculate the factor of safety with the mean, and we have a relatively small uncertainty, as illustrated here, so a factor of safety of 1.5, relatively small uncertainty on the strength, we find that the probability of failure is relatively small, as represented by that blue area down there. However, if we now do the same, but with a relatively large uncertainty, we've got a factor of safety of 1.5, but a much greater likelihood of failure. So same factor of safety, dramatically different probabilities of failure. Not all factors of safety are created the same. And this can lead to the situation where you have a false sense of security about your factor of safety. For example, here's an illustration of a situation where we had a factor of safety calculated with the mean that's 1.4, but is relatively certain, or a lower uncertainty, and one calculated with a factor of safety of almost 1.8, but with a much wider uncertainty. The probability of failure is actually much higher for that higher calculated factor of safety. So things that enter into shortcomings with the deterministic method. Judgments regarding seepage. What's the significance of seepage? We typically would have judged that based on clarity of the seepage flow rate, how piezometer changed. But we wouldn't really look into the characteristics of the dam and the foundation and see if there were vulnerabilities within that structure that could lead to problems with internal erosion. Sounds like we've got somebody who's got their phone line open and making a little noise. So if you're on the phone, please make sure you're muted. Thank you. So magnitude of consequences, a very big factor. Think about a dam has an annual probability of failure of 0.001, 1 in 1,000. but the estimated life loss is 1. And the annual life loss risk is 0.001. Compare that to a dam that has a much lower estimated probability of failure, but much higher consequences. And its annualized life loss risk is even higher. So 2 orders of magnitude less likely to fail poses an order of magnitude higher risk. Deterministic methods really can't address that very well. So in summary, deterministic analysis looks at typically a nominal case or a design criteria scenario without considering the entire spectrum of plausible outcomes, doesn't quantify likelihoods or consequences. Whereas risk analysis tries to look at the range of possibilities and their likelihoods and their consequences. So using risk analysis doesn't mean abandoning our traditional methods, but rather using them to support the analysis in more balanced decisions, in my view anyway. Current risk analysis, I'm going to go through this very quickly. You've heard a lot about this earlier in the week. The federal agencies, almost all of the federal agencies now are incorporating some form of risk analysis, particularly the federal dam owning agencies like the Bureau of Reclamation, the Corps, and other Department of Interior agencies, heard of TVA. The Federal Energy Regulatory, the FERC, is now sort of the first regulatory agency that regulates dams owned by others at the federal level that's moving into risk, and you heard about that earlier in the week. The USDA, NRCS, also does not own dams but helps build them, and it has incorporated risk into some of its considerations and requirements on its sponsors. So the overwhelming majority of dams in the U.S. are not either owned by the federal government or regulated by the federal government. They're regulated by the states. So what's been going outside the federal sector? Well, what's been going on is a number of states have begun to use risk. Colorado and New Mexico are using a semi-quantitative risk analysis approach now, SQRA, on their portfolios. I happen to know those two because I've been involved in those. You've heard several other states this week that are moving more in that direction, and the new assistance program from FEMA for Dam Safety Rehabilitation Assistance Program, I think, is helping to encourage that, which I think is great. And after the Oroville Spillway incident, California Division of Dam Safety is now moving to formally bring risk into its consideration. There have been a number of other non-federal dam owners who found risk to have a value in informing their decisions from a business case purpose. That what are their risks that they're exposing their businesses to, and how can risk analysis help them better manage those risks and reduce those risks going forward. Risk analysis, one thing I did want to mention is sometimes people think and react to risk analysis seeing some of the substantial studies that are done by the Bureau of Reclamation and the Corps of Engineers and others and think that it's just too much effort, that they can't afford to do that. And I want to point out that we really have developed methods that are pretty scalable. Levels 1, 2, and 3 of FERC's risk analysis approaches are versions of semi-quantitative risk analysis that can be scaled up and down to your needs. And full quantitative risk analysis can also be scaled to meet the level of effort that's needed for the decision. So it doesn't all need to be big and scary, and we can do this work without it breaking the bank, if you like. Few examples of risk analysis outcomes, or outcomes that have resulted from risk analysis that work that has been done. Bureau of Reclamation, a paper that Karen Knight presented in the GeoRisk conference in 2017, she noted that after their experience of about 20 years of using risk analysis, Reclamation believed that they had a much improved understanding of the strengths and vulnerabilities of their dams. They were able to better target their investigations, studies, and monitoring so that they were making better use of their funds for those activities. And they also saw a reduction in focus on the rare hydrologic events and rare earthquakes that they had been doing a lot of efforts on, spending a lot of their dam rehab money on, because you could quantify them, and more modifications and risk reductions done for things like internal erosion that were vulnerabilities that were there every day, but were harder to quantify against factor of safety or other quantitative criteria. Overall, they felt they were doing a better job of prioritizing their available funds. Similar observations from the Corps of Engineers on their experience: an increased percentage of modifications for internal erosion, more effective use of available funding, and overall a much more thorough understanding of its dams. And a quote from Eric Halpin, who you heard earlier, and Eric made reference to this, that by employing a risk-based approach, they were able to avoid spending a lot of money on things that might have been pretty low risk and applying money to things that were higher risk within their portfolio. A couple other specific examples that I was involved in, I think, highlight the range of benefit of risk analysis. Beginning with a screening level risk analysis that was done by the U.S. Fish and Wildlife Service, a Department of Interior agency, and they try to follow as best they can the guidance of the Bureau of Reclamation and the leadership of the Bureau of Reclamation. And what they wanted to do is they have a portfolio of about 30 high and significant hazard dams. They wanted to get some sense of the risk profile of that portfolio. They didn't have the resources to do, at least to do in an expeditious fashion, full qualitative risk analysis for all of those 30 dams, but they wanted to get an idea of what kind of risk profile they might have. So they developed a semi-quantitative screening level risk analysis process, adapting it from a method that had been used earlier by the Bureau of Reclamation, and I'll explain a little bit about how they did that and what came out of the work that they did. They have subsequently actually moved on, and they are moving through their system doing qualitative risk analysis, moving through some of the higher risk dams to the lower risk dams, and will eventually do QRA on all of their dams. But the approach they took is they created a spreadsheet-based system, a simplification of an earlier reclamation method. It was semi-quantitative. It included specific consideration of consequences, PFMs for the different loading conditions, and it was then, for an individual dam, each of these PFMs was assessed and placed onto a screening level matrix, which is shown here with the likelihood of failure for categories on the vertical scale on the left, and consequences in 4 categories on the right. And for each failure mode, they would put it into one of these boxes. And this matrix system actually overlays on the guidelines, on Reclamation's guidelines that they were using at that time. Generally, the green boxes are down here below the guidelines the Reclamation was using, the red above, and then the orange sort of in the middle of the guideline range. So a sort of green, yellow, red scale for scaling these. They then also used a scoring system, which I worked together to develop with them, where in each box we put a score, a numerical score. And for all the failure modes, we would add them up to get a total numerical score for the dam. So in a semi-quantitative sort of way, the thing I want to point out to you is note that this score ranges over a wide range, an orders of magnitude range, from 0 for the box down here in the lower left to 300 for the upper right box. And that's following along in that, if you remember on the risk guidelines, angled guidelines that cross across the risk guidelines here are lines of constant annual life loss risk, and they increase from order of magnitude as you go from one block intersection to the next block intersection. So we wanted to be sure that this system reflected that order of magnitude sort of greater concern as you move from the lower left to the upper right. So we put pretty big scores in there. We then, in implementing this, completed a spreadsheet for all of their dams, 29 at that time that we did. This was a desktop exercise in the office. Fortunately, Fish and Wildlife had an active dam safety program for over 25 years at the time we did this. So they had good records of inspection reports, emergency action plans, operating procedures, design and investigation, and construction records, and engineering studies and reports. We used all of those to select likelihoods and consequence categories. For each individual dam, we would come up with, in this case, you can see there are, I think it's 4 or 5 failure modes here, some in this box in the lower left, some in the box in the above it, and some a bit above that. And the white numbers are the actual score numbers. So you can see for this particular dam, it totaled to a score of about 9. They then did that for all of their dams, and we created a table where we had a total score for each dam. As you can see in this table, we have a total score column here, totaling up all of the failure modes. We could indicate how many of those or what percentage of that score came from static, hydrologic, or seismic. And we also could give some sense of how many of them were in the green range, the orange range, and the red range. And from that, Fish and Wildlife could then look at their profile overall and decide where their greatest risks were, where they wanted to spend their resources in further investigation and analysis, and perhaps ultimately further dam safety risk reduction efforts. The service really was quite happy with that. It provided them with a good basis for making their decisions. They've continued to use it. They update it with their annual inspections. And as I said, have now moved forward to doing more detailed quantitative risk analysis on their high and significant hazard dams. The other example is that one that was taken on by a water agency. That water agency being Denver Water in Denver, Colorado, supplies much of the metropolitan area of Denver. They had a high hazard dam, Antero Dam, located in the mountains of Colorado, constructed a long time ago in 1909. It was under state regulation. It had a long history of seepage and actually was under a reservoir restriction at the time this study was taken, and had been under that reservoir restriction for decades. And Denver Water was trying to decide what risk this really pertained to the dam, and whether they wanted to do risk reduction efforts to try to recover that storage. Denver Water chose to do this because they thought it would better inform their management of the risks that were posed by the dam, so they would understand that better. And they also, management might then better understand or better evaluate the investment that might be required to restore that risk or restore that storage and reduce the risk. So it was done as a qualitative risk analysis, facilitated qualitative risk analysis. I facilitated that for Denver Water with a group of experts. We considered the full range of potential failure modes and loadings. Participants included the owner, the consultants, and state regulator. The results indicated that the risk indeed did exceed the reclamation guidelines and that modifications were appropriate. The risk analysis was beneficial to Denver Water, and it did help them get the support from management for the dam safety modifications. The dam has subsequently been modified and the storage capability restored. And it was a pretty streamlined effort, and relative cost was good, and the benefit of the modifications to Denver Water were quite positive. Denver Water actually has since expanded this and has been doing risk analysis for other dams in its portfolio, and as an owner, even though it had not been required at the time to do it, found it to be very beneficial. I'll move on to a few of my thoughts on changes to dam safety practice and how risk analysis has changed our practice. So go back again and remember, what were we doing before risk analysis? We would be doing visual inspections for signs of distress. We would complete analysis, compare them to deterministic criteria. There really, in my view, wasn't a lack of consensus on seepage and internal erosion. Some people would see seepage, and as long as it wasn't turbid or muddy at the time of observation, they wouldn't be concerned about it, but wouldn't dig into whether it could be symptomatic of something more serious. And some failure modes just weren't being thought about at all. What risk analysis has led us to, I believe, is a more holistic approach. We really think harder about how a dam might fail. and what the vulnerabilities of a particular structure might be. And doing that, we come away with a much improved understanding of vulnerabilities that a dam might have and what we need to be paying attention to. Consequences explicitly recognized. It was mentioned earlier in the week that in the United States, basically any dam that has the potential for one life being lost if it were to fail is a high hazard dam. And there's no distinction between a dam that might put 10 people at risk and one that might put 100,000 people at risk. Other international entities, Canada, for example, and Australia, have sort of separated that out into different levels of consequences, with 1 to 10 life loss being lower consequence level than one with 1,000 or more life loss. And I think that makes sense, and it's really time for the United States to do that, but risk analysis explicitly considers that. And we need to remember that for the same probability of failure, a dam with greater consequences does indeed pose greater risk if it has the same probability of failure as a dam with less consequences. So it's important to consider that, and I think risk analysis and risk-informed decision-making has highlighted that. I think it's improved prioritization. Before risk analysis were widely used, there was a lot of emphasis on earthquake and flood hazards, and not always the emphasis on that day-to-day internal erosion risk that could be there present and may be the greater risk. I think we're focusing our limited resources better than we were before. In large portfolios of dams, we can start to prioritize them and go after the largest risk first, and then work our way down through the portfolio. Again, managing that balance between the rare event risk and the everyday risk. I think it's also improved our surveillance methods. Understanding our failure modes and understanding the greatest vulnerabilities of the dam, we can focus more of our surveillance and instrumental monitoring activities on those vulnerabilities of the structure, and use those funds and those efforts better. And it also, I think, has improved our evaluation and modification of alternatives, and this was mentioned in earlier presentations too. Once we identify that we have a risk reduction that we think needs to be done, we can look at the different alternatives, and we can look at them from a risk and probability standpoint and try to get the best bang for the buck in the greatest risk reduction for the investment. And the detailed understanding of failure modes really helps us make more robust risk reduction modifications, I believe. So a couple of key takeaways to leave with you. Risk analysis, I think, is a more holistic approach to dam safety based on potential failure modes rather than deterministic criteria. I think that that holistic approach is really an improvement. Others have talked about we need improvements in the way we do some of our quantitative risk analysis, and there are uncertainties, there are ways that we could be more confident in what we're doing, and that's all true, I agree, but I think this holistic approach is a tremendous benefit. The long-standing deterministic methods, we're not walking away from them. We use them to support the risk analysis. We just recognize more explicitly the uncertainties in those analyses. Reclamation and the Corps of Engineers have developed some pretty well-established protocols for doing the analysis. Both of those agencies, as well as others, are still working on improving them, and I think they will get better. And lastly, risk analysis are scalable, and they don't have to all be big, scary efforts. We can scale them to what we really want to do. So with that, I think we've got time maybe for a question or two if there's anything out there, Joel.
Yeah, thank you very much for the presentation. I think it was a good summary on what we're seeing as risk analysis is implemented and how it's changing decision making, design, and those kind of things. Yes, we do have essentially two questions here. Jose Hernandez asked the question, those values within the risk matrix, risk indices, basically, in other words, adding individual risk indices from the tree failure modes to yield the total risk index for each dam.
I'm looking through that
John,
question. Yeah, I hear it. I'm trying to. The numbers in that we used in the matrix were really just to put a relative weight on failure modes for the box that they fall in, and to make it big enough that that we really would get order of magnitude differences as we move from level to level, from lower left to upper right. So they're just a tool to sort of be able to add together for a particular dam with multiple failure modes to get a sort of total risk index by having the one number or the numbers in the individual boxes.
Okay. I think the second question was from Bruce Rogers. As far as, do you know if U.S. Forestry Service has started risk assessments of their dams?
Yeah, Bruce, I don't know specifically what the Forest Service has been doing and is doing. I think I had heard that they were trying to introduce risk into their program somewhat, but I don't know how much. And I think, as you know, they're unfortunately probably one of the most under-resourced dam safety programs that we have in the federal side, and it would be nice if they probably had some more resources to do more than perhaps they're doing. Perhaps there are others who know what Forest Service is doing and could respond in the chat box with that knowledge.
It looks like Kelly Brom, she said, we do not yet have a formalized risk program. So, so I think that's good for questions for now. I know there's one more that we didn't answer here. We'll probably keep it for the panel to kind of discuss. So thank you very much, John. Our next presenter is Sean Atkelson. I think I'm saying that wrong again, but Sean, you will forgive me and help me correct that.
My name is Sean Askelson. You did a pretty good job of pronouncing my name. I'm a hydraulic engineer with the Corps of Engineers. I've been with the Corps for 21 years, and I've been the H&H branch chief for 2 years now. A little bit about who we are. Portland District. Here's a map that I don't intend anybody to be able to read, but we're part of the Northwest Division. Our district covers portions of Oregon, Southwest Washington, Northern California, and a little bit of Nevada. We have many different missions throughout our district, from dredging to maintenance of coastal ports. We operate the Lower Columbia River projects, so Bonneville, The Dalles, John Day. We have projects in the Klamath River Basin. We have projects in the Willamette Basin, which I'll speak about today, and some projects up on Mount St. Helens. Our authorized purposes range from navigation, flood risk management, power production, hydropower, recreation, environmental, including fish and wildlife missions, irrigation, and water supply. A little bit more about the smart people that are actually doing most of this work. Portland District H&H has 4 branches. We're within the Engineering and Construction Division. We are one of the 4 branches on the H&H side, and 3 sections contributed significantly to the information I'm presenting today. Those are river and hydrologic engineering, reservoir regulation and water quality, and dam and levee safety. Within the branch, we have about 55 full-time equivalent employees. Most are engineers and scientists, so we like to geek out on this stuff. And our duties range from rainfall runoff analysis all the way through the dam and levee safety program. I will freely admit that most of the work today has been developed by my staff, so and a lot of them are on the call today, so I want to thank them while I'm going through this, and if I get any challenging technical questions, I will definitely deflect to them. The discussion today about Detroit Dam, we have It's one of the 13 projects in the Willamette River Basin. And we actually operate the Willamette River Basin for flood risk management as a system. So all these projects store water during storm events to attenuate the floods going downstream. There are regulating points downstream of Detroit that we have to hit to make sure we don't flood out the tributary, but we also have regulating points on the Willamette River system. Our authorized purposes specifically at Detroit are flood risk management, hydropower navigation, fish and wildlife. I'm not going to read the rest of them, but you can see what's there. And some of the key statistics, the project was built in 1953. It's 450 feet tall, just shy of 1,500 feet in length. Pretty good drainage area, 438 square miles. We protect about 77,000 feet. We do have 2 operating units. We have 6 spillway gates, which I'll be talking about today. And we have 4 regulating outlets at 2 different elevations at the project. Okay, next year. At the project, we operate based off of a rule curve, what we term as a rule curve. And what it does is it balances the flood risk management mission with all other authorized purposes. We break down the rule curve into 3 major periods. We have a major flood season, which means we're low in the winter. That extends from the beginning of December all the way through the beginning of January when we expect, the beginning of November through the beginning of January, where we expect our major winter storms to come through. We have a conservation storage season, so starting on January 31st, we start filling to try to fill the pool for summer for meeting other authorized purposes. And then once we're full, we have conservation release period throughout the summer, and we use that primarily to meet biological opinion requirements. We have fairly regimented operations, so we have a water control manual that dictates release levels. They're particularly detailed and prescribed during flood risk management operations. And if we do have a chance to operate different than the water control manual dictates, we need to get a deviation to that water control manual, which is approved through our water management chain to the regional level, which is our Northwest Division office. I mentioned the biological opinion or BIOP. It typically dictates lower level releases for fish and wildlife needs, some different ramp rates downstream, so how quickly we can raise stream elevations and lower stream elevations, and what we need to do to maintain adequate dissolved oxygen levels. And as I mentioned before, regulation points downstream are in the North Santiam, and further downstream in the Willamette River systems as we're operating the 13 projects as a combined system. Some of the work on the Detroit spillway gates that we needed to do. We had some trunnion friction issues at Detroit, which is similar to a lot of our other projects in the Willamette Valley. And so in all 6 gates, we had to replace our trunnion bearing pins. That actually requires, taking those pins out of the trunnions and having the gate hang free for an extended period of time, resurfacing that bearing and inserting a new bearing surface. Again, in addition to that, we had some other structural improvements we needed to make, structural reinforcements. So you can see those are highlighted in red, where we're actually going to add stiffeners to the spillway gates, and then we were going to paint these structures. On the mechanical side, on each pier, we're going to remove the existing operating equipment, so the hoists and lift mechanisms. We had a little bit of concrete demolition, a little bit of pier work that we had to do while we're doing that, and then get these mechanical systems back in place. We had some power supply and controls issues that we needed to take care of, but 95% of those were complete during the first construction season. Some of the challenges that we have at Detroit, that the project was not built with bulkheads or bulkhead slots. So we really have no way to keep the water from coming up onto the spillway gate if Mother Nature chooses to give us that water. Because of the proximity to Salem, it makes for an attractive recreation location. There's many businesses that rely on the high pool elevations during the summer to support their restaurants, marinas, and so forth. So it's heavily dependent on getting the pool filled every year. We do have biological requirements, which include flows, but also temperature control. we do have a reservoir that stratifies, and so we need to be able to get the pool up above spillway crest and hold it there for as long as we can so we can evacuate a lot of that warm water to try to reproduce the pre-dam conditions downstream. While we were doing this work, we anticipated at any given time we could have the pin out for removal between 10 and 14 days in the field. A little look at our reservoir regulation over 60 years, approximately 60 years. You can see we've got 3 lines drawn there. The purple line, which is a minimum, which isn't really important, and then the green line, which is average. And anybody who's in the H&H field knows that average isn't a good indication. What we were really looking at were the red dots were the maximum pool elevations over the last 60 years. You can note that from the start of summer, our maximum pool elevations are generally pretty predictable. And as we go through October and November, even up to mid-December, we have fairly predictable and fairly reasonable maximum pool rates. As we get to later December and into January and February, into our major flood control season, you can see that those high pool rates can vary drastically. So those are what we were really looking at in terms of finding a good operational window. The forecasts that we have in the basin, we do have 10-day forecasts that are available, but those forecasts are really only reliable out to 3 days. We do monitor real-time snowpack and reservoir elevations, but we have a little bit of unknown coming at us, even though we do have forecasts available. So remember earlier I said we had a 14-day pin outage period where this gate would be set up on blocks and unstable. Well, we really only have 10 days of forecast, and we can really only trust it for 3 days. So we were in a little bit of a spot to try to figure out how to do this work safely. What we ended up doing before we had the fire, we created a deviation, and we broke that deviation down into 3 construction periods. Those construction periods ran from 14th of November through 15th of February. The first part of that period, all gates would remain on seal. Gates 4, 5, and 6 would be inoperable because of the way our mechanical equipment works. If we're working on gate 5, it shares equipment loads with what's on gate 4, so gate 4 would be inoperable. During that time, we had full use of reservoir storage, although we do know we would have reduced spillway capacity because we couldn't operate those gates. But this was early in the year through November when things were fairly predictable, and we did not need the spillway capacity. As the work progressed, we would take 2 gates up off a seal, and we'd block them up for the strengthening and pin replacement work. We had worked out an agreement with the contractor that they would have 72-hour notice, and if we gave them 72-hour notice that our 10-day forecast was looking bad and our 3-day forecast was looking bad, and we're going to inundate them with reservoir water on the pool side, they would have to lower the gates back onto seal. And then during that period, we would actually have, at 1 gate at a time, be able to remove the trunnion pin. So the gate would be up off a seal and no pins in place, so we actually couldn't rotate it out of position for up to 2 periods, and we would do those sequentially. To mitigate some of those risks, we asked the contractor to have a temporary pin on site. So if we did see a 72-hour window where they'd have to put the pin back in, they would be able to do that and lower the gate with the existing mechanical equipment. And then when the mechanical equipment was being worked on, we had the contractor develop a gate lowering system. So while the gates blocked up, if we needed to get those back down, they would actually be able to lower them. We would be able to hold pool during that period, but we wouldn't be able to pass water through those gates. And then as a condition of our deviation, we were going to closely monitor the weather and pool for the duration of the work. So we have folks twice a week provide updates to all of our district and division management, including the construction and contractor, letting them know what our forecast looks like, letting them know what the weather patterns are showing, if we have an atmospheric river heading into our basin, if we're going to have rain on spill events is what we were really looking for. We did some contingency planning. If we had a big event coming at us, we would look at double the event and see if we still had flexibility while we weren't required to handle that double capacity, we did want to know what kind of factor of safety we were dealing with. And I'm happy to say during the 2019-2020 construction window, the weather really cooperated and the contractor did a great job. We were able to get through that work very successfully in the first construction season. What we had during August and September of 2020 was some unprecedented wildfires, at least from our recent records. The figure on the top shows all the wildfires we've had in the basin from 1985 to 2018, which are, they're significant areas, but they weren't as drastic as we saw in 2020. A couple statistics we saw from 2020, we burned about 40% of the area upstream of the Detroit project. It might be a little bit hard to read, but the Brighton Bush region, we had 78% of that basin burned, about 25% of the headwaters, and 30% of Blowout Creek. Downstream of the project, we had about 75% of the area from Detroit to our engaging station burned. So we had pretty significant damage in the entire basin that we were trying to manage. And the tools that we had available to us, we did have good rainfall runoff models that were calibrated to pre-fire conditions. We had an estimate of the wildfire perimeter maps. This fire came through in August and September of 2020, and our construction work was supposed to mobilize in October and really start in earnest in November. So we had to make some pretty tough decisions in a very compressed time frame. Things that we did not have and things that we would not have, good hydraulic models upstream of Big Cliff, so between Detroit Dam and the next downstream dam, which is only a couple miles, we didn't have a good hydraulic model in that area. We don't have good bathymetry downstream of Big Cliff, and we didn't have really good LIDAR for one of our bigger basins upstream. And I'm going to jump over one slide, let you guys look at this while I talk the next two. Before a fire is the modeling that we have available to us, and during the fire, there are certain conditions that we'd have to be aware of. That really didn't impact our construction sequencing or risk during construction. What we were really looking for is after the fire and during the rain events after the fire, and trying to evaluate the changes in the basin. The things that we chose to be able to look at were the water and the increased runoff from the burn scars. So what we were really looking at was volume. We understood that Detroit would catch more water from a given storm event after the fire compared to before the fire. The timing, so how quickly that water comes into the basin and how much quicker that pool is going to rise. And because we had a significant portion of the unregulated basin burned downstream, we knew we were going to have a more difficult time to mitigate the flooding downstream as we normally would, because the downstream portions are going to be unpredictable. And then we were going to look at the peak flows, just when that inflows increase and how much peakier it would be, knowing that we're going to have to catch more water during those peak hours. The things that we knew we weren't going to be able to do going into this was some of the debris and sediment increases from the burn scars. So we didn't attempt to figure out what the sedimentation, how that's going to reduce channel capacity, how it's going to potentially reduce flood control capacity upstream. We did not attempt to address debris into Big Cliff, so the next operating project downstream, or how that would impact our operations, or the impacts of woody debris downstream and reductions in our spillway flow capacity at Detroit specifically. And so with this said, we do know we have limitations in our analysis. We have no period of record for post-fires analysis within the district, so we don't really know what to expect analysis-wise for a fire this big. Most of the wildfire data we have is from arid regions and not necessarily on the west slopes of the Cascades where we're at right now. Some of the arid regions had said we could predict inflows hundreds of percent more than what we'd expect right now, which was really troubling. But that is the purpose of the analysis. We reached out to the experts at HEC and ERDIC, which is our Engineering Research Design Center, just to see if there was a standard operating procedure or formal guidance for these type of analyses, which there weren't. we know that even when we do our analysis, there's going to be a high amount of engineering judgment that's going to take place. And our best guess was only going to be able to bracket the expected risk. We don't have the tools and we don't have the time to be exact with this. So the best thing we could do was hit it with a big hammer and see what that does and make some relative comparisons. So the questions we decided to ask during the analysis were really three questions. How much will the flows increase at the Detroit pool? What is the increased risk of needing to use the spillway gates during the construction period? And what is the change in overtopping risk that we have with only 3 spillway gates during our major flood risk season? And how much better would it get if we added additional capacity? We used a couple modeling tools available to us. The first one is HEC HMS model, which is a rainfall runoff model. We assumed a couple different variations. One, we assumed all the sub-basin areas are burned. So we knew that wasn't necessarily the case, but said our biggest hammer is we're going to assume everything's burned and how much that's going to change our rainfall runoff scenarios. And then as a fallback, we assumed only the Brighton Bush and the area downstream between Detroit and FEMA are burned, which is similar to what we saw. So it's closer to what we think is going to happen. But instead of drawing a fine line, we said just assume all those basins are burned pretty significantly. We simulated rainfall runoff and stream flows and reservoir operations for our entire period of record, but we chose a few select flood events for a pre-burn and post-burn condition analysis. We have a couple of moderate events that we typically like to track. January 2006, January 97 were moderate events. February 1996 was a pretty significant event, and then we did look at probable maximum flood. The way we were going to look at this was we were going to generalize the changes in flood probability. So we weren't looking for exact analysis. We were looking for general changes in trends based off of some big assumptions we made in the basin upstream. So going to the first question, how much flow, what would the change in flows look like? This is the first analysis, first part of the analysis, looking at the December 96 and January 97 flood events. As you can see here, we did see some changes in the inflow with the entire basin burn. We could get higher peaks and have significant more inflows. But when we start looking at the Detroit pool, while we were able to handle the 96, 97 events under full pool, we anticipated we'd see a little bit of an increase above full pool. When we look at the Mahima control point, that's our regulation control point in the North Santiam. We expect we would be above bank full, but probably be able to hold the pool below flood stage for the most part. Next, we moved on to the January 2006 simulation. And what we see here is we did see some changes in the inflow. The peak was somewhat higher than the pre-fire conditions, but was still within the FRM, or flood risk management limits. And we were seeing that regulation would briefly touch flood stage, but we didn't anticipate to have a big change in flooding downstream due to the fires. Next was February 96, which is a pretty significant event for us. The biggest change here was the infiltration losses. So what we'd assumed before, the pre-fire conditions, we thought we'd get a lot more runoff based off of this because we would not get infiltration. You can see we would have a change in the peak inflow. We would have a slightly higher peak than pre-fire conditions. And this one, depending on how the extent of the burn area upstream, we could be facing some significant challenging regulation needs under the worst case scenarios. Lastly, we looked at probable maximum flood simulations. And what we saw here are that the losses are relatively small under a PMF simulation. Really, it was the change in the hydrograph that has a little bit more effect, and it's more of an effect on the timing. The results from the pool analysis showed we'd be similar to pre-fire conditions, and we'd be within reasonable FRM pool levels. Regulation could be challenging if the results are on the extreme end of these simulations. So that was good news. You know, we spent a lot of time looking at the inflows and decided we could handle the inflows, we could handle the increase in pool, and we would not significantly increase flooding downstream because of the fires. The next question we had was, what is the increase in needing to use the spillway gates? So as I said before, we can't isolate these gates from the pool. The contractor's plan included putting the gates up off a sill and blocking them up off of, so they would not stop flow. And then there would be a period of time there where they could actually be pushed into the forebay if the pool came up at the wrong time. Remember, this is targeted during the October, November, and mid-December timeframe. So we're looking at earlier in our flood season. When we reach spillway crest, what we needed to do is have the contractor lower the gates and put them on seal for two purposes. One, to stop the flow from going downstream and limiting risk to the gates. What we were looking for were impacts to construction and the temporary platforms. They had a lot of wooden platforms in the pool, so as the pool came up, if we got to that level, they could potentially lose some equipment and lose their work platforms. To do this analysis, we used RMC, the Risk Management Center's RFA model, to see what our change in chances are of rising above the spillway crest. And the probabilities are higher enough that a period of record analysis could inform. So we sent our HYA, our hydrology folks, after that. A little note about the RFA model. It's a reservoir stage frequency curve with uncertainty bounds that utilize a deterministic flood routing while treating the inflow volume, inflow flood shape, seasonal occurrence of the flood event, and antecedent reservoir stage as uncertain variables rather than fixed values. That's a fancy way of saying that we did a Monte Carlo simulation and sampled the various ranges of probability of all those different factors and came up with a series of curves. So we're really looking at an ensemble collection at the changes of within the basin based on the conditions we've given it. And you can see here the expected probability of reaching spillway crest. Before it was burned in the winter, there was a somewhat high probability, probably about 5%, but before it was, but during the construction period where our gates would be off sill, it was fairly low. When we started looking at the burn scenarios, the medium and high, we saw some significant increases in those relatively, but nothing that we saw changes in the major flood season, but not significant changes during the November timeframe when the gates were going to be off a sill. So that made us feel a little bit more comfortable with that analysis. The last thing we did is we looked at the post-burn conditions, and we looked at November for our historic period of record. And when I say historic, this is, you'll see 85 years, and the dam's not that old, but this is a water record. So we put in the 85 years we have of water conditions throughout the system and evaluated those conditions. And what we saw, post-burn event, there would be two, before the burn, we would have no events that would reach the spillway crest in November while we're doing the pin outage work. And after the burn event, we could see two events out of 85 water years that would reach the spillway crest. Those would be 1950, which was actually before the dam was completed, and 1973, which we do have good project information from within the dam's time frame. What we determined is there is adequate storage in the reservoir and adequate outlet capacity to take a single gate out of service for this construction period. There is an increased likelihood that there's going to be a need to close that gate during the pin work. We don't think it's going to be a storage capacity issue or a regulation issue because we could get that gate down on sill within 72 hours with the provisions in place. And then we had a good monitoring plan and good coordination to continue moving those projects forward. So ultimately, we decided we could go forward with a pin-out period starting with gate 4 and potentially moving to gate 3 if conditions remain favorable throughout the season. The last question we were asked is, what is the change in overtopping risk with only having 3 spillway gates through a major flood season? So in the beginning, we had assumed, our analysis said we could be safe with 3 spillway gates for a major flood season, but we know the basin has changed. So how much better does it get with 4 gates or 5 gates? So really trying to figure out if we could take 2 gates out through the season, which was the contractor's plan, or if we needed to have a little bit more redundancy in gates going forward. And remember, this is only looking at the relative change in probability. This isn't exact, and we're not accounting for debris blockage during an event in this analysis specifically. What we see here, looking at our graphs, our expected probability of overtopping with 3 gates, the pre-burn conditions, the no burn, very, very low probability that we would overtop with 3 gates. When we start looking at medium burn conditions, so 2 of the basins significantly burn, that increase went up a little bit during November, and it went up a little bit more during winter. And then if we looked at the high burn scenario, we saw kind of a significant increase, assuming only 3 gates. So we took it a step further. And this is only looking at the high burn probability scenario. So this is a far outlier. The 3 gates is copied down there. Again, we didn't bother to look at a 2-gate scenario because that wasn't going to be approved in the first place. We could get it back down to almost no risk if we went to 5 gates, which we didn't think was practical, but we found a good set point at 4 gates. It turned out 4 operating gates through a major flood season was similar to, in the post-fire condition, was similar to the risk we were taking for 3 gates during our previous analysis before it burned. What we resulted in is a deviation, and I'll walk through a little bit of how this deviation changed from pre-fire to post-fire. The first thing we had to do was finish our mechanical and electric pier work on gates 5 and 6. So before we let the contractor take another gate out of service, we had to get our existing gates fully functional. During that time, we would have full use of the reservoir for flood storage, and we'd restore all the capacity we need from the spillway. We would allow the contractor to take 1 gate off a seal for the removal replacement of the trunnion pin. Again, they were allotted a 2-week period for the trunnion pin work. We were restricting them only to work on gate 4. They needed to maintain the temporary pin on site and be able to lower the gate back on sill within 72-hour notice. And then once we had the gate back on sill, we'd have full use of the reservoir flood storage once the gates were all back on seal. And then after the gate pin work was done, we'd have the major flood season, which was 16 January to 1 March. We decided we needed 4 gates, 1 additional gate from our previous deviation through the major flood season. Some of this was from the expected change in runoff conditions from our analysis, but some of it was a practical consideration that we didn't know how the debris was going to change in the reservoir, although we anticipated it would increase, and it would likely increase significantly if we had a major flood. So because it was an unknown, we decided an additional gate for redundancy and potential blockage was in our best interest. Again, we'd have to closely monitor our weather and our pool during the duration of work. We started looking at the anticipated weather events coming at us, and we had a 5-inch weather event as a trigger to where we would start doubling the capacity going forward. Some of the other things that we looked at as potential risk mitigation measures, these were operational. We could draft the pool earlier. So instead of waiting till late in the fall to draft the pool, we could get ahead of it and gain some space. We could stay at minimum pool longer. So instead of February 1st starting to fill the pool, we could actually hold the pool down. It does have some biological impacts and recreation impacts, but from a dam safety and a construction safety standpoint, it was an option. We could draft to minimum power pool. So we do have a little bit of flood storage that's available to us in the power pool. It's not necessarily something we like to do because it's there for weather emergencies like Texas is experiencing right now, but it was an option that was available to us. And then we could increase regulation goal downstream. So instead of regulating strictly to bank full, we could let it encroach up to flood stage a little bit more. These were all operation considerations that we had on our plate and had available to us. None of these have been required for our construction work. The summary. This summary of our findings. We did find a change in peak volume, peak time, and it's going to add stress on Detroit operations, generating higher pools. We do think we're going to have slightly higher flows downstream. So where we thought we'd have minor floods at Detroit, it's likely going to flood a little bit earlier, but nothing that was of major significance. The increase to Detroit was small, so we were able to move forward with the deviation in the construction work. We do know that the inflows are expected to arrive at Detroit a little bit sooner, and we do have some increased risk in rising above spillway crest, overtopping, but adding another gate during the operational season decreases that risk by a factor of 2. So I went pretty fast. That is the end of my presentation. Does anybody have questions, comments, or discussions?
Sean, thank you very much for the presentation. It's very informative. We do have a couple of questions. I'll start with the one from, I think it's Charles Kowitz, and it says, if the pool is high or at the top of the dam, would upstream flooding occur?
Yeah, I appreciate that question. If we did go over the top of the dam, because it is 1,500 feet long, it's a big, long weir, so we gain a lot of additional capacity at that point. So we do not risk upstream flooding from a PMF scenario, but we could have significant changes downstream for overtopping events. So the tributary directly downstream in some of the major metropolis areas further down would be our primary concern.
Good. Then the second question is from Megan. I don't know if you can read this, but as a result of this work or in anticipation of future work, was the cost versus benefit of retrofitting to make bulkhead replacement an option considered?
Yeah, I appreciate that question too. And that's we've been going through these spillway gate repairs at a lot of our projects in the Willamette Valley, and none of our high head flood control projects have bulkheads or bulkhead slots available to them. Some of the early analysis we did as a system was trying to figure out how we could block these off. And one of the complicating factors is once you do have a bulkhead in place, having a crane big enough to get it out of place in case you need the capacity for large events. So it was something that we looked at. We didn't think it was necessarily a feasible solution at any of our projects. Some of it due to our spillway capacity needs, and some of it due to the shape of the piers and the upstream face of the dam. So it was something we considered, but it was ruled out fairly early as a system-wide approach.
Thank you. All right. I think we're 2 minutes over the initial planned time, but I think it's been appreciated to have everybody stay on and presenters staying on later than they expected. So thank you very much, Sean. Thank you.
Thanks.
At this time, just a couple of quick announcements. So we'll be starting up again tomorrow at 11 a.m. Eastern. Just kind of a couple of reminders. We've got your evaluations. If you can fill those out, we'll really appreciate those. And then just filling out the ideas for next year's conference. And then looking forward to tomorrow, we have several presentations that are going to occur, as well as the panel discussion at the end of the day tomorrow. We do have a document that we provided that you can put some questions for the panelists, so we can have those questions as well